Hello, everybody. Good afternoon. It's time to get started. Welcome to Projects Day. I'm Shiny Abraham, Senior Design Coordinator for the Electrical and Computer Engineering projects. And thank you again for joining us today. I know our teams are very excited to share their work with you. And we are delighted that you could join us in celebrating the culmination of their 9-month-long senior design projects. So a few reminders before we get started. There will be time for question and answers after each presentation. And for our live audience, if you have any questions, just raise your hand and we'll bring the microphone to you. For guests joining us via Zoom, if you have any questions, just type them in the chat window and we'll get to them. All right, so I'll hand it over to the first team. We have 3 presentations scheduled for this session. The first 2 presentations are sponsored by the Boeing company, and the third presentation, or the third project, is sponsored by IEEE-PES. So I'll hand it over to the first project team.
Good afternoon. We are Team ECE 24.2. Our project is sponsored by the Boeing company, and our project title is called Desktop-Based Human Model Input Device Using a Depth Camera. My name is Brian Xiong. I'm majoring in electrical engineering.
My name is Gautam Mahesh. I'm majoring in computer engineering.
My name is Jessica Quinville. I'm majoring in electrical engineering.
And I'm Paramveer Singh, and I'm majoring in computer engineering. For our project support team, our project advisor is Dr. Agnieszka Miguel, who is also the EC department chair. Our liaisons are from Boeing Commercial Airplanes, and we've worked primarily with Dr. Jim Troy, Dr. Catherine Meza, and Alma Limon Vichy.
Moving on, our sponsor for this project is the Boeing company. Founded in 1916, Boeing has been an industry leader for both military and commercial aircraft design. As aircraft manufacturing increased over time, there has also been an increased focus on intuitive, efficient, and sustainable manufacturing, designing for manufacturing and maintenance techniques as well as passenger comfort. So that goes into the purpose of our project, where we are tasked with collecting human-posed data so that we can understand ergonomic limitations that goes into designing products. This will mainly be used for safety in manufacturing, maintenance, and as well as passenger comfort within cabins. This is not the first iteration of the project, as we will also be improving in 3 key areas, which are reducing the operational and setup complexity by making the materials easy to source, as well as having the calculations within this program be real time. We are also improving the cost effectiveness per unit by reducing the unit cost to be under $500. And finally, we'll be reducing the size footprint of the whole system to fit on a typical office work desk.
The goal of our project is to capture the pose of a small-scale human figure for use in a digital human modeling environment. We have been suggested by Boeing to capture the joint positions using a depth camera. Therefore, our final output are these joint positions, as can be seen here, marked with circles. These joint positions are given out as XYZ coordinates, and the data is formatted using comma-separated values. There is also 2 different ways of collecting this joint position data. On the left, we have color tracking. On the right, we have media pipe, which is a machine learning model. And I'll go into more detail as to why that is later on.
Moving on, this is a high-level overview of what the joint capture system, joint position capture system does. The first step is that the user will start this joint position tracking code, and once that is started, the user will then articulate the 3D printed figure into a pose that they wish to capture. While this is going on, the camera will continuously capture images and calculate joint positions based off of those image streams. Once all needed joint positions are collected, it will then send this data over using a socket-based connection to a specified endpoint. And at that endpoint, then they can then transfer this data over to a myriad of different applications, such as a virtual 3D human modeling environment.
To track the 3D model, we'll be using the Intel RealSense D405 depth camera. And the reason for this is because this camera meets all the project specifications set by Boeing, which are this camera meets the $500 budget. It has a minimum maximum range of 3 and 30 inches. It has a USB interface for easy connectivity. It's able to capture close to real time with latency of 10 to 100 milliseconds. and it's able to capture with a minimum frame rate of 20 frames per second. One thing good about this camera is that it comes with a built-in RGB camera, and this is good for our project because we'll be able to color the joints of our 3D model and use this RGB camera to track its movements. Finally, this camera offers open SDK support, which means we'll be able to import code library files like OpenCV, which is responsible for tracking the colors, and MediaPipe, which is going to help us track the 22 key points of our 3D model. This is our camera staging design. As you can see, we have the camera tracking the 3D model, and both the model and the camera will be propped up on stands. Behind the model, we have included a black backdrop, and one thing I'd like to note is that the distance between the camera and the 3D model will not always be 300 millimeters, as we'll be constantly moving both the model and the 3D model, and the camera to capture different poses and different positions. However, if we're looking for more of an ideal scenario for testing purposes, we'll be following this staging. This is one of our test setups similar to the last slide. At the back, we have the 3D model, and behind it, we have the black backdrop. The center, the camera is connected via USB and is connected to a Windows 10 PC that is running the detection application and is sending data to the server. In our setup, we have included a black backdrop, and the reason for this is because it provides visual consistency and it blocks out any unwanted objects in the background. For example, the image on the right, figure 8, the camera is tracking the 3D model, and in the background to the left, you can see 2 whiteboard colored marker pens, which are also getting tracked by the camera accidentally. Hence, if we use a black backdrop like shown, we would eliminate these kind of errors. One thing I'd like to highlight is that our black backdrop is made of black felt and is matte black in color. The reason for this is during one of our testings, we realized that matte black reflects the least amount of light as compared to other colors we have. And because of this, it's going to increase the tracking of our camera significantly.
The team decided upon 3D printing as the solution. It's low cost, it's easy to replicate, and easy to adjust. The legs and arms use peg joints with notches on the receiving limb to help create friction. The shoulder and hip use a split sphere with pegs, allowing for a full range of motion. The torso is shelled using a negative 3 millimeter offset. This encapsulates the ball joint, allowing for the figure to be self-supporting. All of the joints are able to lock in place and are movable. We tested with 3 different materials throughout this project. The first one was thermoplastic elastomer, as seen in figure 11A. The next one was polylactic acid, as seen in figure 12. And then the third one was thermoplastic polyurethane, as seen in figure 11C. We also tested different nozzle temperatures, and we tested different printing speeds. We found that a speed of 20 millimeters per second at a temperature of 240 degrees Celsius worked best for TPE. We found for PLA that a speed of 50 millimeters per second with a temperature of 220 degrees Celsius worked best. The TPU prints, as seen in figure C, were very weak and unreliable, and therefore we did not use it. There are also 3 tests conducted after the print is completed. The first is a tolerance test to make sure that these pieces fit together properly. The second is a range of motion test to make sure that it reaches the desired ranges of motion, and a friction test to make sure if over repeated movement, the pieces still fit together as they should. The shoulder and hip use PLA. This allows for optimal rotation and extension. The arms and legs use PLA, which is solid for bending and stability. The torso and neck use a ball joint using TPE. This allows for bending and rotation. The head uses PLA, and it's a realistic human head model to help with the orientation of media pipe. These are 2 possible poses that the figure can lock in. The figure can lock in any pose that a human with a full range of motion can.
So to summarize the printing of our 3D model, we'll be using 2 different types of filaments, PLA and TPE. Majority of our 3D model will be printed out in white PLA, and on the other hand, our stand extender will be printed out in black to match the color of the black backdrop. As you can see in the center of the table, we have included all the printing specifications, which will be used for both the slicer and the 3D printer for different filament types and different body parts.
The primary piece of software for this project is the joint position tracking software. It provides joint position data in real-world units, which are measured in meters. I would like to point out that this joint position data is given with the scale of a human and not the scale of the figure. This is due to the limitations of media pipe. Here we have a reference model of some key points we would like to track. One of them is marked with this red circle. Therefore, all of these points that are these zeros up here are different joint positions we would like to measure. This data is given out as XYZ format. Furthermore, this is coded using the Python programming language, as it allows for easy integration with code libraries such as OpenCV, MediaPipe, and RealSense. The primary purpose of this software is to compile all the joint position data and send it to the server using a CSV format using a socket connection. As I mentioned previously, MediaPipe as a machine learning model is a pre-trained model that is developed by Google that can track human pose in an image. It provides joint position data in both image normalized and joint and real-world units, which are in meters. Here we have an image of the MediaPipe model. It can track up to 33 key points. However, we are not using most of these, such as these facial features and these features on the hands. However, we're also missing some points here, such as in the spine region, and for that reason, we're using a hybrid approach of using color tracking to fulfill those requirements. We're using the OpenCV code library that is used for image processing tasks for this purpose, as it can allow for color tracking and color detection. Using the color tracking, we can supplement MediaPipe to get these necessary joint positions. We also use the RealSense SDK, which allows to connect to the camera and pull the depth to these color markers. Once we get the data for all these color markers, we're able to translate that into the same units and coordinate space as the MediaPipe model. Here we have a demonstration video of the tracking server running. We first put in the host name followed by the port number. Then we can press enter, and then the triggers and the software starts running. On the left, we have the color tracking. On the right, we have the MediaPipe. In the background, the data is continuously transmitted, and the figure, when adjusted, can also take care of the tracking as well. Speaking of the data receiving software, we use this to parse the CSV string into an array of coordinates. It also handles updating the array whenever new data is received. Currently, it prints out the data to the console window to better preview the data and show the data transfer as completed. Here we have a video showing the data server, and the data comes in real time in real speed. It is 22 key points. However, we will only look at one of them here. So if we look at one of them, we can see here that we have 4 major components. First, we have the unique marker ID to identify which joint we're looking at, followed by 3 coordinates, so X, Y, Z in units of meters.
From the joint position tracking program, we wanted to highlight 2 different results that we got from testing. One of them was the accuracy of these joint positions. As seen on the images on the right, we can see the pose of the figure as well as a plot of the joint position data received when tracking this figure. Some of the highlights from this are that the head and the lower feet are not entirely accurate to the pose being measured. This is most likely due to MediaPipe tracking on a 3D printed figure rather than it being tracking a human. As a result, this leads to discrepancies and MediaPipe making the wrong assumptions on where the joint positions might be rather than where they actually are. This can be rectified by 2 different recommendations, which are to train a model specifically on the figure itself, which could lead to more accurate joint positions being recorded, or to modify the figure proportions to match MediaPipe expectations while not removing the degrees of freedom already present within the figure itself. Next up, we want to address the confidence of the joint positions being recorded. On the table on the slide, we can see that on the last 3 columns, they are the standard deviation of joint position, select few joint positions over 50 different iterations. The maximum deviance that we received from this test was around 2.8 centimeters of deviance over 50 iterations. Keep in mind that the pose data being measured is in the scale of the human, as said by Paramveer. So when taking that into context, the actual deviance of the joint positions over 50 iterations is not as large as expected.
The total budget spent by the team was $848. The per unit cost was $391. The reason for this difference being we tried different backdrops, we also bought multiple stands, we tried different 3D printing materials, and that accounts for the extra $500. In summary, the 3D figure is printed in TPE and PLA and can lock in any position that a real human with full range of motion can. The joint tracking software tracks 22 key landmarkers in real time, and the data is transmitted to a server using socket connections. There is also a visualization tool to help monitor the joint position accuracy. This will be used for controlling a virtual human model in a 3D modeling environment to help with constraints and ergonomic design. And to improve the accuracy of our project, a new model can be trained on a 3D figure, or the 3D figure proportions can be adjusted to fit media pipe's expectations. Here are our references. Any questions?
Great presentation, thank you guys. Quick question, I might have missed this. Was the performance results that you guys got within the requirements that were specified by the project team? Or was there a requirement on performance?
Yeah, so there was no required, there was no set performance metric that we wanted to match. However, our main goal for this was to improve on the ease of use for tracking these, for capturing the pose of the figure, but also to make this real-time system done so that it has a high refresh rate, so that if a user adjusts the pose of the figure, it's able to recalculate those joint positions in a timely manner as well. But as for the expectations for what our benchmarks for time and real-time calculations, there was no set expectations for that.
And you guys were happy with the results?
Yes, we were.
I was going to ask a follow-on, but I forgot. Okay, thank you.
Yeah.
Great presentation. I was wondering. Great presentation. I was wondering if you have any data on the performance of the color of the spine.
So can you repeat that question again, please?
Yeah. So I recall that because the model that you use don't track the spine joints, right?
Yes.
So you use color, some color sticker to track those joints. What's the accuracy of that method versus the standard method that you use?
For that, if we look back here at the standard deviation, we have one of those color markers here. So we have one of those red markers here, and it's very accurate with that. So there is little to no issue with standard deviation, and it's very accurate with those. The issue occurs with the media pipe and some points.
I see. So it seems like there are certain deterministic solution to this problem. Can you talk a bit about why you choose an approximation in using machine learning for the other joints?
Yes, because we use machine learning, specifically media pipe, for this, as it allows for an easy integration with Python, and it got almost all of the necessary joint positions we would like to track. So in this reference model, we have these additional, these wrists, the elbows, and the shoulders. And all of these points were part of the media pipe model here. So we use this. Furthermore, this model is open source and we can use it, and it does not have any strict licensing.
All right. Thank you for your answers.
Yes.
We have a question from Zoom. What is the real-world use of this project?
So the real-world use of this project is it allows for easy capture of the joint position. So instead of adjusting sliders on a virtual screen, we could adjust the physical model as we saw in the demonstration video here. It's more it allows for easier feel to feel if we can adjust it to a certain position, and allows it to easily transfer it over into the virtual environment. As having a input device that is actually which you can actually manipulate, is far easier to and less cumbersome than adjusting sliders on a screen. Yeah.
And then for real-world applications, can also be used kind of like, in the cabin, so trying to decide like what is the spacing you can do between seats that'll still make it comfortable for the other passengers, as well as maintenance constraints. So can a maintenance man reach this certain part, or is there a different type of design that they're going to have to do instead?
Excellent presentation, thank you. I had a question about, did you correct for the curvature or the potential error that might be introduced, the curvature of the lens? Or did you calibrate for that?
So for the depth measured, there's actually two different types of depth that we are utilizing with this program. So we mentioned that we had to translate over the color track joints over to a media pipe. The media pipe model, the way how it calculates depth. The reason being for that is that the camera calculates depth based on the distance from the camera. If a camera was a plane, it'd be the distance away from the camera to the image itself, while media pipe uses an origin point on the figure, which originates at the midpoint of the hips, and it bases the z-axis off of the deviance from that value. So the x, y, and z coordinates are all based off of that origin point. For media pipe, the lens curvature, we did not, both for media pipe and RealSense, we did not account for the curvature, as we were more concerned about making the data uniform with each other rather than, and we did not test that edge case for this project.
Thank you for all the questions, and let's thank the team again.
Hello everyone, we are one of the capstone teams sponsored by Boeing this year, and we're also known as the CS2404 Boeing Non-Motion Safety Application Team. We're very excited to have everyone here today, so let's get started. So our student team consists of 4 people. We got Mia Lee over there, Nahom Kefeleng right here, Erickson Kajo, and myself, Sergio Satyabrata. Our sponsors are Chris Esposito, Catherine Meza, Rohan Rana. We got Jim Troy over there. We got Jeff Heiserman, Kevin Puterbach, and our advisor is Professor Lisa Milkowski. And so here's an overview of what we'll be doing today. I just did the introduction, and then we'll be going on to the problem statement or the opportunities next. Afterwards, we'll be talking about the major deliverables that we have set out at the start of our capstone year, and then after that, we'll be talking about what we have done in the past 3 quarters. And so within Boeing factories, workers sometimes find themselves in secluded, isolated, and even low signal areas. And so this causes a safety concern as they may be unable to find help in case of an accident. And so the current safety solutions may not be 100% adequate to ensure a swift response in these type of environments. And so we propose on enhancing a mobile application that was built by last year's CS Boeing team. And Essentially, our application is to monitor the worker's activity, and let's say, and it'll also alert relevant personnel in case, like, let's say if the person were to not move or when they deviate from usual work activities. And so some of the major deliverables that we wanted to talk about is the upgrade of the motion sensing algorithm. We wanted to decrease the amount of false positives and false negatives within our application. Next, we wanted to implement some sort of continuous check-in system where we can effectively communicate the worker's safety status to relevant personnel. And then next, we wanted to investigate into Bluetooth for some sort of location tracking purposes. And then lastly, we want to investigate into the audible alarm technology, which is basically a physical alarm placed in these high-risk areas. And so when a worker were to, let's say, get injured, the physical alarm will sound off, and then it will, hopefully, people nearby will help this worker. And next, I will pass the microphone to Mia.
All right. Thank you, Sergio, for that. So just as Sergio said, one of our major deliverables for this year was improving upon the past team's motion sensing algorithm. And so when our team first got this app, we were exploring it, and we noticed that the motion detection was really sensitive, which is great for non-motion detection, but we noticed that it was giving us a lot of false positives in the motion sensing algorithm, meaning that instead it would trigger for hazardous fall events, but it would also alert in just daily living activities such as jumping or walking around. And so that made our team's primary focus, reducing the number of false positives. So just like last year's team, our algorithm is a threshold-based detection algorithm that primarily relies on the phone's built-in accelerometer to detect a fall event. However, our team also implemented the gyroscope within the motion sensing just to give another threshold that data values must pass in order for an event to count as a fall. And then instead of just looking at one threshold window, we are now looking at two threshold windows. So basically that means instead of just looking at the impact of a fall, we are also looking at what happens after the fall. So this next slide has just an example of one of our test cases that we're doing. This shows an actual fall acceleration here with the blue line. We have two different windows that we're concerned with. We have the red box here, which is the triggering time window, and then the second box, which is green, that we call that the checking time window. And for this test case, both algorithms would pass. So with our first algorithm, the previous team's algorithm, it would look at the red box, sees that the blue line passes the height right there, and then the alert is called because it counts as a fall, and that is correct. For our new algorithm, we also have to check the green box. So it sees same thing, it says that the blue line goes above the height of the red box, but then it also checks the green box and sees that the blue line does not deviate from the height. It stays within that green box, and that means that it is a fall. So that would also be correct. This is another one of our test cases for someone who is kneeling down. This is a case where we do not want the alert to trigger because it is just someone kneeling down. It is not considered hazardous. And this is where our previous algorithm fails. So the previous algorithm looks at the red box, sees that the blue line goes below it, and then the alert is triggered, and we don't want that to happen. So with our new algorithm, it looks and sees that the blue line passes below the red box, and then it also just has to go through the green box again. It sees that the blue line goes above the height of the green box, and then it does not call the alert, and it does not recognize that as a fall, which is correct. All right.
Thank you for that, Mia. So we'll be talking about how we're going to be testing this. So there are two types of tests that we are concluding, which is the motion and non-motion testing. And we have also conducted it with a humanoid test dummy, which is designed to replicate the falls to ensure the safety of our team members while testing it. And how it works is we have a phone, and we're going to insert it into our pocket, especially the dummy's pocket, if we were to use the dummy. And when we were to drop it, it's going to record the data, which is then recorded into a table of test suites, which is used for further analysis and further use. And Mia here will show you how our test works, as you can see here.
All right, thank you, Erickson. So this is just one of our test cases as a demo. This is where we want the alert to trigger. So you can see the phone in real time on the left, and then our video on the right, you see the dummy drop right there. And then you see a pop-up confirmation window. So this pop-up confirmation is triggered when a fall alert is recognized, and that just gives the user a little bit of time if they want to cancel the alert from sending. And then, so we still count this as a success. And then, this is one test where we do not want the alert to trigger. So if you see the video here, Sergio is going to start the detection, and he's going to put the phone in his pocket and pretend to trip over, but not actually fall down. So he trips right there. And then when he takes the phone out of his pocket, you see that there is no pop-up confirmation window. So it correctly identifies that that is not a fall event. All right. And then, so this is a chart showing our results from our tests that we have all done. And this is where we do not want the alert to trigger. So you can see that the new algorithm here in red matches pretty well with the ideal case, the perfect algorithm here in yellow. This is what we want it to do. And then it performs, you can see over there on the right, it performs a lot better than the old algorithm in blue, because the old algorithm is still calling the alert when we do not want it to. The reason why you don't see the blue bar for the other test cases here, because we wanted to prioritize testing the new algorithm for our team due to time constraints. All right, and now I'm going to pass it on to Nahom, who's going to talk about our next major deliverable, the alert system.
Thanks, Mia. So the alert system, or the communication system, is how our application sends and receives the user safety updates, and how that information is managed and used to display alerts when danger is detected. It is crucial that this system is fast and reliable, since it ensures that workers in danger get the appropriate attention as soon as possible. Okay. So the major part of our project was implementing a new alert system and making sure that it was fast and reliable. When last year's team designed and implemented the non-motion safety application, they used a message-based alert system. So basically, they send out messages in the form of alerts using Fire-based messaging system. And if the application detects motion danger or non-motion danger, or if the emergency button was triggered within the application, they sent out the messages in the form of alerts. This implementation did not allow for the real-time monitoring of a user's safety status. So it also had other shortcomings, like some latency from Fire-based messaging service, the complete failure of the whole system when the application was disconnected from the internet or the physical device was not functioning properly. So our team designed and implemented a new continuous check-in alert system that allows for the real-time monitoring of a user's safety status. So we used a real-time database where the application will send the status updates of the user continuously, and people who are monitoring that user through the application will get those updates in real time. The first thing this has allowed us to do is to let the users choose if they want to be sharing their status. So, for example, the picture you see here is of our homepage, and the first toggle button you see is to let the user choose if they want the motion algorithm to be running, the motion sensing algorithm. The second toggle button is for the status updater, where the user could choose if they want to be sharing their status or not. Since our application sends out the status updates of the user continuously, people who are monitoring the users can now tell if the user is online or offline or in danger, which is displayed in the application. And they can also tell if the worker is disconnected, and it lets them know that they will not be receiving any status updates from the user. This is especially important for workers who may be working in environments that do not have network coverage, or if the environment they work in has signal interference. The picture on the screen right now is of our workers page. This is one of the most important pages in the application. This is where a person monitoring other users will be most engaged with. So as you can see, a user can use this page and add other users using their user ID. Once they add them, they get instant access to their real-time safety status if the person is sharing it. So for example, we have 3 users here. Preceding their name, you can see a small logo which is a quick way to show if the person is, the status of the person. And if we wanted, for example here, Mia is online, Sergio is disconnected, and Nahom is in danger. If we wanted to get more information on that person's safety status, we can click on their name. For example, if we click on Naham's name, since he may be in danger, we could see more information about why, how the danger was caused, or what triggered the danger alert, and the timestamp that it was that the danger alert was triggered. So what this allows is this implementation also allows us to share other information if we wanted to. For example, future teams can add additional information, which it could be shared within the status updates. Next, we'll be moving on to the investigation into Bluetooth for location tracking. Sergio will take over for that.
Thank you for that, Nahom. So the reason why I wanted to investigate Bluetooth is because we wanted some sort of location tracking within the application. So last year, the previous Boeing team, or the previous CS Boeing team, implemented the GPS, but they soon found out that once they entered an aircraft within the factories, they lose all type of signals. So like, no, there's no Wi-Fi, there's no cellular data. And so we wanted some sort of technology that doesn't require cellular data or Wi-Fi, and hence why we came up with Bluetooth. And so the two candidates that we were researching was the Bluetooth Low Energy and the Ultra Wideband. So Bluetooth Low Energy, or BLE for short, has a range of up to 100 meters, and it can transmit data of up to 1 megabits per second. And it uses very low energy so that it doesn't consume much power. On the other hand, Ultra Wideband, or UWB for short, uses quite a lot of power. But at the same time, it also has quite a short range, up to 10 meters long. But it can transmit data from hundreds of megabits per second up to several gigabits per second. And so we wanted to do a bit more than just investigate. We wanted to implement this architecture. So we actually made a Bluetooth peer-to-peer architecture, but due to time constraints, we were unable to. So we plan on passing this down to the next Boeing team. I will now pass the microphone to Erickson.
Thank you for that, Sergio. So speaking of Bluetooth and Bluetooth Low Energy, I would like to introduce everyone to feasibility for a physical alarm. Now, the reason why we're doing this is so that we can improve the alert system greatly by implementing something like a physical alarm. And by doing so, in our feasibility tests, we have used a third-party application called BLE Scanner, as you can see over here, which is present in the App Store. And how this works is we have two devices, particularly Android devices, where we use them to look at the approximate latency along with the distance of the devices in general, where it'll emulate basically a physical alarm and the worker in the particular area in general. And the best part about this is that we are not using Wi-Fi. We're currently using Bluetooth, as we would like to experiment with the technology further. Now, unfortunately, the results are unsatisfactory due to the fact that we cannot reach a conclusion with this. And moving on to what we have covered up so far, we have covered the fact that we have created an alert system that allows continuous status updates, and we have improved the motion sensing algorithm greatly, and we have launched an in-depth investigation into BLE and UWB, Bluetooth Low Energy, Ultra Wideband, and we have also conducted a feasibility test for the physical alarm. And here are our references. Now, thank you. Any questions?
Hello. I had a question. What about some kind of thing where the worker goes still without a violent fall? Is that part of the requirements? And did you address that?
Yeah, so we have two different kind of like fall detection or motion sensing. So we have motion detection and we have non-motion detection. What you're talking about is the non-motion detection, where someone is staying still for a really long time, and that would also be concerning just as like a fall, right? So the past team worked really hard on the non-motion detection, and we were pretty satisfied with that because it was really sensitive to motion. So if you're staying still, it would detect that, and then if you moved a little bit or you're moving around still, it would still say that you are safe. So that is one of the tests that we are looking at too. Yeah.
All right, thank you.
Here, get him and then over to you.
Hi there. I have two questions. First question is, say the user forgets their phone. Is this capable of pairing up with another smart device?
Okay.
We haven't worked for any implementation for like pairing with other devices, but it was one of the ideas we had when we were investigating into using Bluetooth, so we can have like a peer-to-peer kind of alert system. But we did not work on anything like that.
Okay, that goes into my second question. So, have you looked into the alternatives such as like the NFC as opposed to Bluetooth?
Yes, we did. In the beginning of our project, we looked into a lot of alternatives into seeing how we can, like, that. We looked into that mainly for real-time location tracking, since GPS is not really reliable in the factories. But we did not move forward with that, no.
Yeah, you showed ultra band. I mean, what's the spectrum in the Bluetooth, that ultra band spectrum?
I believe it's 3.1 gigahertz up to 5 gigahertz. Right?
Okay.
Yeah.
Thank you.
Jim, do you want to add anything? We're lucky we have Jim Troy in the audience, one of our technical leaders in this space.
Yeah, I guess we could say for one of the devices we talked about, maybe like a Fitbit kind of thing is another thing, but we kind of concentrated on the phones because that was what most people had available. They didn't want to require others to buy additional hardware, so that was one of the ideas. But it is a good point. If you forgot your phone, you're unprotected, so it might be good to have a device.
Excuse me. Please use a microphone because we have a Zoom audience, so they can't hear and they don't know what's going on.
Oh,
That was my fault.
Actually, I would like to add on to your smartwatch thing or external device. So we at first we wanted to our idea was to get a smartphone paired up with a phone, but then we realized that let's say if you were to bang on a table or like you bang your hand on something, it'll cause some vibrations, right? So it'll probably most likely raise the alert, and then we don't want that. And so we also realized that it will be quite difficult to adjust the algorithm.
Thank you. We are out of time for questions, but if you have more questions for the team, please find them at their poster after all the presentations. All right. Thank you, team. Do we have the next? Please come on, camera.
Hi everyone, we're Team ECE 24.3 and our project is the Microgrid Prefeasibility Tool.
Hello, I'm Aziz. I'm a computer engineering major.
I'm Daniel. I'm studying electrical engineering.
Hello, my name is Masad. I'm an electrical engineering major.
And my name is Serena and I'm studying electrical engineering as well.
And an introduction to our project liaison, Dr. Peter Donhauer, as well as our faculty advisor, Dr. Shruti Singh.
So our project sponsor is the IEEE PES, Sustainable Energy Systems for Developing Communities, also known as SESDC, and they're a working group within the IEEE PES organization that crafts and sustainable energy solutions for many issues, and one of the primary concerns is energy access issues. And so the primary goals are to research and then also facilitate information exchange with different entities, such as the researchers, those in industry, and public policymakers to ultimately enact change. So they also focus on the overall sustainability dimensions for both grid-connected and off-grid connected solutions. So there are over 770 million people in the world who do not have access to electricity. Ultimately, that is a major issue, and all those individuals experience energy poverty. So energy poverty has a wide-ranging list of repercussions. It impacts things such as the overall healthcare access in those areas. It impacts the economic stability. It impacts the educational opportunities. And overall, it impacts the quality of life in these areas. So implementing an off-grid system, which is a small power grid, or that gives electricity to these areas, is ultimately really crucial and vital. However, the pre-feasibility tools on the market that ultimately assess the technological and financial needs of these areas are so expensive that it's ultimately pose a huge barrier, a financial barrier for these individuals. So our team was tasked to develop a microgrid pre-feasibility tool that assesses off-grid electricity access projects and that can be made in a free and open source manner that ultimately bridges the gap and ultimately can be used to solve help energy poverty. So our tool calculates and presents the energy impact, and then also can be used to educate and support the community once the electricity access project is implemented.
So for a quick application breakdown, there's 5 major components, as you can see. First component is the front end. That's where the user actually interacts with our tool and application, where they can input data, just kind of interact, download any sort of data, see visualizations. You have our back end. This is our section that actually communicates with our database. The front end handles scripts to and from the server to the front end. We then have our actual project scripts that actually do the simulations and calculations. From there, we have graph generation. So not only does the user actually see and receive like a CSV file and just numbers, they can also see a graph representation of their simulation. And our final results are then packaged, delivered to the front end, and presented to the user. So for a list of project resources and tools, we've used DigitalOcean for our actual server hosting and database management. Homer Energy was used for validation for our tool, since that's pretty much the #1 and major tool for assessing electrical grids. React Native was what we went with for our front end, Django for our back end, PostgreSQL for our database, and our simulations were all developed in Python. And so for our back-end features, we were able to develop account creation and login. So accounts are created using email, password, and username. Passwords are encrypted and saved in a database. Project creation and saving, since multiple groups may service multiple communities, they might have a separate project for each community. You can separate them, save them, come back to them. Script processing, so again, any of our scripts that run our simulations handles data from those scripts, including SCV filing, or CSV filing, file processing and handling, and we have a REST API as a little package it up. We also have our server for our backend. As mentioned before, it is hosted on DigitalOcean, along with their managed database. The reason we went with this was it's very easy to upgrade if needed. Currently, we don't need a very powerful server. It might be possible as time goes on. Very easy and cost-effective to upgrade. Also, support from DigitalOcean. After talking with them, they're pretty intrigued with the project and are willing to provide technical engineers for assistance, along with a $200 credit, which is enough at current cost to run the entire application for about 10 months. And build deployments easier on DigitalOcean, quite easy to actually kind of set it up.
So we did a lot of progress this quarter on the front-end development. As you can see here, this is an image of the homepage that the user first sees when they first go onto our website. As you can see in the first highlight of the red box, that's the navigation bar. And when the user presses the home button, they can get to this page. And then they can also learn more about the project and then kind of sign in and get to their user profile. Likewise, on the top right-hand corner, we have the design section, which is where the user is going to implement all the major inputs for the calculations. And then in the results section, they'll see all the calculations and the graphs that are associated with that. And then finally, when they go into the profile, they can learn more about their user, such as the email, their location, the project number, and so forth. And so this is a little more in-depth onto the login page. The user can log in, and likewise on the user profile, they can learn about the project number and the project location and such. And this is the design page when the user goes in to input all the major calculations. And so the left-hand side is the design, and the right-hand side is the results section. And so as you can see, there's two red boxes. That's going to allow the user to click on the different calculations when they want to input, and then they can see the output on that other side. And finally, here's our demo of the current progress that our team has done so far. So this is the home page that you can see, and then when the user clicks on the login page, they get led to it. And then the design section, they can click on the various inputs and add all the inputs that are pertinent to their system. Likewise, we can input the hourly load data. And then finally, the user is led to the results page where they can see all the graphs and appropriate scripts and the plots for them. And then finally, there's the profile page that shows user information about their current system and their project. And yeah.
So when a user decides to create a project, they're going to be prompted to enter a daily load profile. And with that information, we can have an idea of how the load is going to look like over a month. And then we can also apply seasonal variations to the load to see how the load is going to look like over a year. And then we also can run a simulation that can span over multiple years. So figure 1 is showing the image of an annual load profile, and figure 2 is showing the image of a 10-year load profile. Likewise, the user is going to be prompted to decide what sort of energy sources they would like the simulation to be based upon. Is it going to be solar? Is it going to be wind? Or is it going to be an hybrid system with a combination of wind, solar, and diesel? And then the simulation is going to be emulating the operation of an off-grid system. And for each hour, we're going to be checking for instances of surplus as well as instances of deficit. So when there is a surplus, it means that for that hour, we're producing more energy than we have consumption for. And the surplus energy is going to be used to charge the batteries in the storage system. And when we check for instances of deficit, it means that for that hour, we're not producing enough energy to serve the load. And first, we check if the storage system is able to pick up the deficit, and if not, we have to bring in the backup generator to sort of serve the load as well as charging the storage system simultaneously. So this is a solar system simulation that we ran for Malawi. And as you can see on the graph, you've got the storage in reds, you've got the loads in orange, and you've got the surplus and the deficit in green. So what you're seeing is that the solar energy, which is in blue, you can even barely see it, which is an indication that for that location, the solar system may not be suitable. Next, for the very same location, what you see is in blue, you've got the wind energy, which is an indication that wind energy, you may have more wind energy for this location if you use wind energy rather than use solar energy. And also, you have the ability to decide to go with an hybrid system with a combination of solar, wind, and diesel. And when the system finishes to run, the results are going to be printed to a CSV file, which is going to be available to the user to download and sort of have an understanding of how the system is going to look like. So a very short breakdown of what the results are going to be about is you get a summary of the solar energy that's available. You get the summary of the winds. You also get the diesel energy that's available at the time. You have a summary of the load consumption. You have the surplus and deficit information. You also see how much is available in your storage system. And for that hour, it also shows you if any energy has been curtailed. You also see if for a particular hour you were not able to meet any load demand. And the generator status is just telling you that for that hour you are using diesel energy.
Okay, so moving on to the cost aspect of the project, we've taken the approach of a levelized cost of energy. What that is basically taking the total lifetime cost and dividing it by the total energy output. The total lifetime cost consists of the initial capital, the cost of operation and maintenance, the cost of fuel, as well as any other disposable costs. And moreover, it compares the cost effectiveness of different types of energies. As for the revenue aspect, the calculation is done on a 25-year span basis. It is stored in a CSV file for the user to view in much more deeper detail. It also contains a monthly as well as a yearly net revenue, and at the very end of that CSV file, it shows you a 25-year net revenue value. And it also includes a breakage and report analysis of equipment depending on the components.
So when it comes to project validation, we've decided to use Homer Energy to sort of cross-reference the results. So this is a wind system simulation that we ran using Homer Energy. And you see that the yearly output energy is listed at 51,246 kilowatt hour. And when we run the same simulation using our design, we see that the yearly output energy is 52,160 and 90.90 kilowatt hour. So we were given a 5% margin of error, and when you can see that this is about a 2% percentage error, which checks the results. Next, you also did the same thing with a solar simulation, and in this case, the yearly energy output was listed at 10,157 kilowatt hour, and when we cross-reference the results with our simulation, we see that the result is at 11,177.88. This is about the 5% margin that was given to us. It's about 10% of a difference, and the difference was mainly because of the fact that we didn't have all the necessary information that we needed to properly calculate the solar energy. Information such as the pivot tilt and temperature value were not available to us, justifying the such a big percentage error.
So alongside the validation of the energy, we are looking here at the validation of the costs. What you're looking at is a cost validation of Homer with a 10 kilowatt wind turbine system. And what we're looking for here exactly is the levelized cost of energy at $4.36. If we look at the results that we have, it turned out to be $4.12, which comes out to be in the acceptable 5% error margin.
So when it comes to major project milestones, we spent first quarter, a lot of it with project planning. Towards the end of the first quarter and going into the second quarter, we worked on the actual application website design. At the very start of the second quarter is when we worked on the back end, started working on our computed graphs, our scripts, and as we were doing those, we were also doing internal validation as we went along. And spring quarter was when we were combining components. The only thing we wish we could have hit was testing with intended users, which we're going to work with our liaison to give to communities that actually would have used it, taking their feedback and implementing it. We're hoping for the next group to continue with that.
And then when you look at the left-hand side, we see the anticipated budget that we had for the beginning of the year. It consisted of a Homer Energy license, AWS services, parking, as well as a GitHub team plan. And when you look at the right-hand side, we have a hosting services from DigitalOcean, as well as a Homer Energy license. And we see a 43% decrease from the anticipated budget compared to what we have now.
So in terms of next steps, we did a lot of progress this quarter. However, we weren't able to implement all of that into our front end. And so we suggest that the next team that works on this continues on implementing all the major components that we've created and integrating it all together. We also suggest that the next team works on testing its tool with its intended users and then using all that feedback that's gathered through the testing to make a better version of the application. So we all grew a lot this quarter just doing this project, and we just wanted to share some things in terms of our personal growth. So for me, I learned a lot about project management and how to handle and implement all the different skills that I've learned in my 4 years as an electrical engineering student and put it all together and use all the resourcefulness for this project.
So for me personally, working on this project, there was really a lot of moving parts that needed to come together to work together. And you sometimes hit a road and you have to learn about learning at a problem from different angles to see the solution that can work for you. And I think that's a really good skill to have as an engineer.
For me, it was a lot of the web aspect. We're electrical and computer engineers, so we don't work as much on web stuff. So it was a new learning experience.
And as for me, my personal growth out of this senior design capstone, I believe Daniel can agree with me over here. Curtailment was a big milestone for this project, and it was a difficult concept to understand at first, but we were glad that we got it to work. And these are the citations that we've used. And thank you for your time. Do we have any questions?
Yes, so I was wondering, how is the maturity of your model compared to what's remaining in the actual, like the software application development?
I would say that we're basically trying to create a software that's similar to Homer Energy. So Homer Energy is really sophisticated as a model. So I think we're just in the early stages of having a functional model that's similar to Homer Energy as well.
So you think you have work to do on the model of the power and consumption and sources, as well as completing the front end and some of the just system pieces?
Yeah, I think that there are some of the calculations that we're doing that are just like on the basic level, and when you compare that with Homer, it's more sophisticated in a way that it uses advanced metric. And I think that the step that's going to have to come forward for the next group is to try to get it to be as close as possible to Homer Energy.
Thank you.
We have a Zoom question. Will this be released for public use or only corporate use?
No, 100% free and for public. If a company like a corporation does want to use it, they're fully free to use it, but there's no intention to take a penny for the use of this application.
Additionally, this application is on the website, on the web now, and so it's basically available right now, but we just need to make it into a usable state for more users to fully get the most out of this application.
All right. Thank you, team. This brings us to the end of session 1. And if you have any questions for the three teams that presented in the first session, please find them at the posters after all the presentations. So thank you again for attending, and the next session begins at 2 o'clock. itself is like a 3-minute warning. I'll show you. I'll be sitting right there.
Oh, don't worry. Oh, we're totally.
Microphone test. Can you hear me? Good.
Have worked throughout the year on challenging real-world projects from external partners. The students applied technical knowledge from coursework and gained skills in project management, teamwork, budgeting, technical writing, and oral communications. Projects Day is the culmination of their experience.
Seattle University and the Project Center and the way that they like to tie in
Test,
projects
test.
and industry into their senior
Test,
design
test.
projects, I think is really excellent.
They can learn from the professionals and the experience while they're in school.
The professionalism of the engineering staff, the willingness to mentor students that are within a university environment still, bring them into more of a career-driven aspect with the project.
So the value of working with a student group, I think, it's on both sides. It's helping them gain real-world experience. It's helping us get a project done that we really need.
Because it's taking a big problem and using a team of engineers to break it down into smaller problems.
It's a great sort of way for students to learn real-world sort of engineering constraints that they have not thought of when they're working on textbook problems.
I think it's a really great way to get young engineers, engineering students involved in the real world before they graduate.
The work on this project definitely is going to help my career. Definitely learned a lot of new skills that I didn't have before.
It's just a really great learning experience for me because you're going to have a lot of different failures in life. Just enjoy the learning process component of it really helped me, I believe, to just set the tone for the rest of my years at Seattle University and eventually transitioning to my professional career.
The skills I've gained from that, the teamwork, communication skills, have really set me up well for the future.
Right, let's get started. Welcome to session 2 of Project Day presentations. We have 3 teams scheduled to present in this session. The first project sponsor is Sound Transit, and the second and the third project sponsors are Amazon. A few quick reminders before we get started. We have time for question and answers at the end of every presentation. And for our live audience, if you have any questions, just raise your hand and we'll bring the microphone to you. And for guests joining us via Zoom, just type your question in the chat window and we'll get to them. All right, so I'll hand it over to the first team.
Alrighty, well, good afternoon, everyone. We're team EC 24.5, and today we're presenting our HVAC monitoring retrofit project. Before we jump into things, I'd like to introduce our engineering team. Today we're joined by Camille Rose Valencia, myself, Sean Syria, Tian Tran, and Shin Ford. And throughout this project, we're guided by our project faculty advisor, Dr. Shiny Abraham. Throughout this project, we've also had the opportunity to work with some of our sponsors' engineers, which include our most awesome liaisons, Drew Peters and Craig Delala. And our sponsor for this project is Sound Transit. So Sound Transit began operations in 1993 as the Central Puget Sound Regional Transit Authority. Their services encompass the King, Snohomish, and Pierce counties, offering 4 main forms of transportation, which include the Link Light Rail, the T-Line, the Sounder trains, and the Sound Transit Express buses. And to quantify the significance of the Link Light Rail, approximately 75,000 people commute using the Link Light Rail every day, which sums up to tens of millions of riders every year.
So the Tukwila International Boulevard Station and Seattle-Tacoma Airport Station are 2 of the regional stations of the Link Light Rail service. Their communication room housed the crucial equipment that keep the train operation running smoothly. However, due to the old infrastructure, these rooms are not up to Sound Transit current standard for monitoring. The heating, ventilation, and air conditioning system, or HVAC for short, play a crucial role in maintaining the environmental conditions within this space. But up until now, the only way to determine this condition required a technician to be physically on site for inspections. To address the concern, Sound Transit had reached out to the engineering student team, EC 24.5, and requested a solution to retrofit this station communication room with the remote monitoring capability. So what is the motivation for our project? As many of you know, the Link Light Rail system is lifeline for Seattle, serving millions of passengers throughout the years. These passengers rely on the service to get to work, school, important event, and back home to their loved ones. Any disruption, even minor, can cause significant delay, inconvenience, and frustration for the riders. Our proposed solution is not only about technologies, it's also about the commitment to our community for a smoother and more reliable service in daily commute. With this system in play, technicians can quickly respond to any issues, reducing delay and keeping the train running on time. And this ensures that everyone in Seattle who rely on the Link Light Rail service can continue to do so without worry. So given the request for solution by Sound Transit, our team has come in with our project goal to create a system that collects and analyzes data pertaining to the environmental condition within the Tukwila International Boulevard Station and SeaTac communication room. Integrate this data into Sound Transit building management system and alert technician in case of emergency conditions.
All right, so here's a look at our hardware design. Figure 4 here shows our general functional flow block diagram of our system. So working from left to right, we have our standard wall outlet, which provides 120 volts AC, which then gets converted to 24 volts DC via our power supply to power the main components of our system, namely the temperature and humidity sensor and our PLC. In addition to that, we have 2 layers of power fail-safe protection. As you can see, we have a circuit breaker as the first layer, and the second layer consists of 2 fuses. And we also have a junction box in between the sensor and the PLC to house those important connections. And lastly, we have our PLC and the client laptop running G Simplicity connected via an Ethernet network switch to establish communication. So Figure 5 here shows our prototype for our in-lab setup. It basically follows everything that you saw in Figure 4, but it is excluding the 2 fuses and the junction box. So the PLC, or the Programmable Logic Controller, is the brains of our system. So why did we choose the Click Plus PLC CPU and module. So first, the Click PLC is robust for our purposes, and it has a lot of open source documentation. And the module itself has the 4 to 20 milliamp analog inputs that we need for our sensor. So it is very compatible, and that is why we chose it.
Here you can see the final version of our system that we created for our on-site installations at the CTAC and TIB stations. So the image on the left shows the junction box and the sensor, and the image on the right shows our back panel setup. To make this back panel setup, we essentially just took everything off of our prototype board and put them directly onto the DIN rails, making sure to include those terminal fuse blocks that Camille has previously discussed. Of note, you can notice that the terminal blocks and the wires are of specific colors. Those orange blocks are used for data connections, while the gray ones are used for power connections. All those gray wires are used in accordance to Sound Transit's industrial standards, while the black, white, and green wires are used for ground, neutral, and load connections.
So for our software approach, we implement the server-client-based models using the MAPR TCP/IP communication protocol. During our lab setup, we use a network switch to simulate the Sound Transit server and 2 laptops that act as server and client. Initially, we tested the basic device communications using Python between the 2 computers. And when this was successful, we replaced the server computer with the Click PLC, which we then wrote the program for the server side using the Click programming software, and their client side using G-Simplicity.
All right, so now let's take a look at what's happening within our PLC. So the program that our PLC uses is ladder logic programming, and an example of that can be shown on the figure on your right, which is kind of what it looks like. The main operations that occur within our program are math operations to convert the raw temperature and humidity data to something that's a little bit more readable for our operators. The temperature and humidity sensor that we are using takes the temperature and humidity values and maps it to a current of analog, or maps it to a value of analog current, and that current value is then outputted and received by our sensor. Now, using specific conversion equations, our PLC converts that analog current value and brings it back to the form of temperature and humidity that we're all familiar with today. In addition to these operations, our PLC is also designed to store some additional information, which includes the upper and lower threshold bounds for the acceptable range of our measured variables. So again, our temperature and humidity values, and as well as some characteristics of the PLC. So that includes the PLC's IP address, subnet mask, and even the PLC status. All of these values are stored in holding registers, which can be written to and read from. And this ability to read and write from these holding registers will play a significant role in the team's accomplishment of our stretch goal, which we will cover more in depth later on in the presentation.
So on the client end, as requested as part of project scope, we work with the G-Simplicity, which is a supervisory control and data acquisition software, or SCADA for short, to handle the data coming from the PLC. So we specifically use this G-Simplicity to simulate the client end that our system communicate with and to visualize data on the platform. And to establish the operations, we need to define 3 basic elements, which is the port, device, and point. Respectively, these 3 elements will address the questions of how do we communicate, which device are we talking to, and what information do we need from the PLC. And here is a quick look to the G-Simplicity workbench where you can access the port, device, and points that I previously mentioned.
Next, we're going to briefly discuss the process that we took for installing our system at the Tukwila International Boulevard station. So first, we did an inspection of the site to ensure that we knew exactly where in the station we wanted to put our junction box, sensor, and the back panel inside the electrical cabinet. Next, we took measurements to see how far the wires and conduits would have to travel to go from the junction box across the wire trays and down into the electrical cabinets to meet the back panel. After that, we cut the wires and conduits down to size, ensuring to leave at least a foot on both so that after we installed everything, we had plenty of material to work with. Following that, we installed the parts. So this involved us drilling the sensor and the junction box into the wall first, and then installing the wires and conduits into that end. After that, we strung the conduits over the wire trays and down into the electrical cabinets. At this point, we cut the wires once more to ensure that they terminated right where the junction or where the back panel was. And then we installed that end of the wires into the back panel, put all the labels on, cleaned up our wiring, and then did some final testing to ensure that everything was running smoothly. Here is a look at our final installation after the fact. So the image on the left shows the back panel with all of the labels, and the image on the right shows the junction box and the sensor that have been drilled into the wall.
So as part of our stretch goal, we created a graphical user interface for the data to be accessible by technicians. Our final products deliver a total of 5 screens, which include 1 main screen and 2 sets of diagnostic and room condition screen. From the main screen, you can see in figure 19 here, is allow the users to access the individual screen of each station. And next we have the diagnostic screen, as you can see in figure 20. This allows the users to diagnose the PLC working conditions by display a series of system information that's stored in the PLC system data register. And finally, we have the room condition screen, which allows the user to monitor the measurement of the temperature and humidity through a range of different features, including the real-time reading display in numerical form and bar level form. The alarm indicator will be flashing red when the measurement is outside of acceptable range. We implemented the Quick Train, which is a built-in features of the software to display the data in a more graphical and detailed manners. And as an additional touch, the screen also allowed the user to reconfigure the threshold by directly changing the low and high values directly from the interface.
Next, we'll take a look at the schedule that we used throughout the course of the project, going from fall to winter to spring quarter. We've summarized all these points into a number of key milestones, with the ones of note being bolded here. So we began in the middle of October with our right-of-way training. This was to ensure that we had permission to go onto site, which we did at the end of October with our first site visit. Jumping all the way ahead to the end of February, we finalized our design plan. Then the beginning of March, we've completed our final prototype. Then in the end of April, we did our final installation at the TIB station.
All right, so here's a cost breakdown of our solution. So as stated, we have 2 sets of our solution, one that's already installed at TIBS and one that will be installed at CTAC at a later time. So our total consumables cost was $513.80. And if we divide that by 2, we get a consumables cost of $256.90. In addition to that, we had our main system components that cost $310.52 to bring us to a grand total of $567.42 per set. So this enables our solution to be at a cost of under $600 for installation.
All right. And now, while the team has outlined some of their accomplishments throughout the year, there are a couple next steps to bring this project to a complete close. The first step is to enable those Ethernet ports on Sound Transit's end. What this will do is to enable that final step of the data flow so that Sound Transit will have remote access to this data, and this will require continued coordination with Sound Transit's IT team to confirm those ports for usage. The next step is to get our last set of our solution installed at the CTAC station. So at the end of our project, the team will be handing over a fully operable and ready to install set to the engineering team to install at an appropriate time.
While this has been a very rewarding project, we also faced some challenges. So the first challenge we faced was learning PLC programming and SCADA graphic design. This is something we didn't learn in our courses, so we had to learn it from the ground up. Another challenge we faced was familiarizing ourselves with industrial automation equipment. None of us had worked with it before, so this was a very interesting experience to do research about it. And lastly, we ran into some administrative factors, such as the lead time to getting a site visit permit and the limited time on the site visit itself.
Over the course of the project, though we did run into many challenges, it was also an incredibly rewarding and teaching experience for us. We picked up a number of technical skills such as PLC programming, learning how to adhere to industrial standards, and developing SCADA software, in addition to a number of field skills during our site visits, such as wire management and adherence to safety protocols. We also picked up a number of soft skills, such as learning how to adapt on the fly, learning how to work together as a team, and sorry. Over the course of the project, we've learned many things, and we had to cut much of the details out of the project or of this presentation for the sake of brevity. So if you would like to learn more, please do visit our booth, and we would love to share more about the project with you. That concludes our presentation. Are there any questions?
One question from the Zoom audience is, what's the sensor's reading range, and is the device modular to allow the user to modify it to suit their requirements while still keeping its reliability?
Can you repeat the question, please?
The first one is, what's the sensor's reading range? Let's start with that.
So the sensor that we use, as I mentioned, it uses the analog current. So that initial range that it measures for is 4 to 20 milliamps. And then,
second? Or
74.
Thank you for the question. So initially we said, like the current one we said right now is about 74 to 76 degrees Fahrenheit. So this is an optimal range for information technology and in general, especially for equipment inside the communication room. For the second question, so as I mentioned during the graphical user interface, that the user can be able to reconfigure the threshold by changing the low and high values directly on the interface itself. So this one will reset the threshold by actually writing to the PLC, which is have two registers that hold the threshold of the temperatures, like the high and low temperatures.
So since the PLC will get connected to the internet eventually, do you guys have any concern about the cybersecurity? For example, maybe someone can trigger a false alarm, and then maybe you need to wait human to go there to check, and then to reset the alarm again.
Seeing as the data will be inputted directly into Sound Transit servers, there's minimal chance of cybersecurity issues unless somebody is able to access Sound Transit servers. What was the follow-up question? What was the other? Oh, that was it? Okay, yeah.
Any other questions? Oh, okay.
Just to kind of follow up on that, one of the features that we like to highlight in our system that it's purely hardwired. So a lot of that communication is done over that Ethernet that we previously talked about. So then that discussion of cybersecurity would be a little bit different if it was, say, over something like a wireless network, like Wi-Fi or Bluetooth.
Excellent. Well, I'm the sponsor, and this is one of the most talented teams that I've worked with, and so I want to thank you all. Excellent work this year. And I did have a question. Were there any challenges integrating that PLC with our SCADA system?
Well, thank you for the praise, Craig. That's a wonderful way to end our presentation. So we did run into the challenge of having a time restriction for connecting our PLC to GE Simplicity because we had the trial version of it. So every run that we had for testing was restricted to 2 hours, and then it would cut off. So, yeah.
Cool. Thank you.
We have time for one more question. Oh my God. Okay.
Thanks so much, guys, for the presentation. Actually, following up on Craig's question as well, I was wondering, I was in the controls and automation industry for a while myself. putting in a brand new sort of PLC with, it seems like that you guys had picked this device in particular. I would imagine that there's an existing set of controls and automation mechanism or equipment already installed on site, and usually it would be simpler path, especially for people who are going to be doing troubleshooting or any modifications in a later point, to use the same sort of device manufacturer or PLC. I'm just wondering if you guys had research on what was existing in the sort of facility, and why did you pick a brand that was not used before?
During the testing and developing portion of our design, we did look into a number of different PLC types. We originally looked at the click because one of our liaisons, Drew, did recommend us to look through a site called Automation Direct, not sponsoring. We really liked the stats of the click. The specs that it provided, everything worked nicely with what we thought we would like. We had also looked at the Arduino Opta, but after we did get our hands on a version of that and tested it, we realized that it didn't work as we thought, and because it was such a new product, it had such little documentation, it wasn't really an optimal choice for us. And at that point, Sound Transit hadn't really given us any, not guidance per se, but they hadn't given us any restrictions on what sort of PLC to use. So because the click at that point was our most researched and what seemed to be the best option, we decided to go ahead with that.
Thank you.
Thank you for all your questions. It is time for us to move on to the next presentation. Thank you, team.
I don't have this plug. The USB. Yeah. Can someone click? Because I don't have a plug for the clicker. There's no clicker, so I'll just click.
Hello everyone, we're Team CS2401 and we're very excited to show you the content moderation tool we made in collaboration with Amazon this year. So next, let's have a look at our agenda. This is our agenda for today. And now let me introduce you to the team. My name is Vanglip Chan, and my team includes Samar Shah, Robert Wajaja, Jerry Shen, and Victor Rashkovic. We also have our esteemed sponsors from Amazon, including Raman, who's at the back, and Henry as well. We also have our amazing advisor, Mike McKee, who's also here. And now let me introduce you to why Amazon came to us and what problems they were facing. We're working specifically with ASCII, Alexa Sensitivity Content Intelligence, which is a team that enforces Alexa's content policies. As such, they have a variety of tools and services that they provide to other Amazon teams to be used. But the current issue they're facing is that a lot of teams want to use ASCII services, but there is a bottleneck where the teams have to be onboarded, and it takes up to 3 to 4 engineering days in order to use their services. As such, it takes a lot of resources and can be very time-consuming. And now I'll pass it on to Victor to share a little bit about our solution.
So first, looking at our team dynamic, we were a very collaborative team. We used the Agile methodology and prioritized communication and customer feedback. The meetings we had with Amazon were very important as they shaped our sprints each time. We had 2-week-long sprints, and we would have 2 meetings as a team each week where we would work on our product as well as discuss any roadblocks. One of these meetings was with our advisor, Mike McKee, who would provide guidance and any sort of feedback that we needed. Our meetings with Amazon were once every 2 weeks on Friday. This is where we would review our previous sprint as well as get feedback on it and then plan our next sprint based on that. We would also communicate via Teams every day. So the product we came up with was a web application where the user would bring their own content and select the APIs they wish to test it against. They could input the content as a singular text file, a CSV file, a JSON file, or an Excel file. Once they input their content and selected the APIs, as well as providing some other configuration, which Robert will discuss later, we would then pass it to the APIs all in the same way. The APIs would return a flag indicating whether the test passed or whether it failed, as well as a confidence score and a category. We would then return these results to the dashboard in an easy-to-interpret way for the user. It is important for the users to be able to re-access old tests and view them. So we made a database where we stored all their previous tests. They could go to the results page on our dashboard, which is where they could view any previous tests. And since there were so many configurations that go into each test, there's a workflow page where they can go back to these and keep working from them or edit them. So the way Amazon will benefit and use our product is that the ASCII team will allow other departments to access this dashboard and test their content against Alexa's policies. Other departments will be able to see whether their content is suitable for Alexa in a much quicker way and through a hands-on approach that will build confidence. The end result is that the ASCII team and the other departments save time and resources, as well as Alexa potentially becoming more widely used across Amazon's departments. Now I'm passing it on to Robert to go over our tools.
So for our tools and technologies, for our front end, we are using React and React testing library to build our application. We're also using Auth0 to provide third-party authentication. And for our backend, we're using Postman for API testing, Node for creating our API routes, and lastly, Mocha and Chai for our backend testing. And for our database, we're using MySQL and hosting it over AWS RDS. So next, looking at our features, starting with the homepage. A user can click one or multiple API or policy options and do a manual input. A manual text entry of utterance, response, context, or locale. Utterance meaning what you say to Alexa. Response is what Alexa says back to you. And context is the previous context of the conversations. And locale is the language that you're speaking to it. Next, we'll be looking at the file page. So in here, a user, similar to the homepage, but instead you are uploading a data set of either CSV, JSON, or Excel files, and it'll automatically fill out the accordion at the bottom. Next, we'll be looking at the results page. In here, once a user checks content either in the homepage or the file page, they will be taken, or they can see their results here in the test page where they can see all the policies that are violated for the utterance. And they can save it as a CSV as well. So next, looking at the workflow. So a workflow is a set of configurations for the home and the file page. So clicking on one or multiple API or policy options and doing a text entries, you can save this as a configuration or a workflow in this case, which will be saved to this page. Clicking on Go will redirect you to the respective pages and automatically fill them out. Next is our user guide page, and here is the FAQ section along with guidelines for the format of how you're meant to upload the data set of CSV, JSON, and Excel files. In here, a user gets to know the purpose of our application. So next, to give a high-level architecture of our application, a user first needs to be authenticated to use all our features. And once a user is authenticated, they can upload their data sets in files or manual text entries. And once they check their content, the responses will be stored in our database in which a user can access it at any time. Next, I'll be passing it on to Jerry to talk about the testing.
Thank you, Robert. So as Robert mentioned before, for our backend testing, we decided to use Mocha and Chai over Jest. It's a simple command line interface for us to get used to, and it also offers high compatibility with our test-driven development
methodologies. And here you can see some examples of our backend testing. And for our front end, we are using React testing library. It also offers a simple CLI interface, so we don't have to go and learn to use another GUI if we had chosen to use Cypress. And you can also see another example here. For our API testing, since we created our API using Postman, we thought it was only natural for us to use Postman again for our API testing. We also created user acceptance tests. User acceptance tests, we gave our sponsors a list of test cases and expected results so they can go ahead and see if our website works as described. They've given us very, very valuable feedbacks that we went ahead and improved our web app on. Next, we are going to show you a short demo. They have the option to either sign up with email and password or continue with Google. After logging in, the user will be led to our home screen, which they can see the navigation to our other pages, as well as our main component, where a user can select a number of policies that they want to test their content against. They can select one by one or select all and deselect all. The user can also input their content. The user also has option to add additional text box, as well as deleting any text box they don't want. The user also has the ability to save workflow, which saves the current configuration of policy selection and content. After clicking on check content, the user waits for the loading to be done. And then they can go to the report page to see their test results. In the test result, we can see the number of API used, number of input that was processed, and the input type, which in this case is manual input. The user can also download the result as a CSV file. If we go to the workflow page, here's where we can see the workflow that we saved. It has the content and our selected policy. If we want to go back and do the alteration, we can click on Go, and it will lead us to this page with all our setup already configured. Next, if we go to the guide page, here's where the user can learn about how to interact with our website. We have a short description of our service. And a quick getting started guide. We also have the file input guidelines for CSV, Excel, and JSON, and an FAQ section. Next, if we go to the file page, here we can see it has the same idea of the home page, where the user can select number of policies they check, upload file in the correct format, either CSV, JSON, or Excel. Then they can either check content or save workflow. If we go to the report page, we'll see now the input type will be changed to CSV. Now I'll pass it on to Summer for the next section.
Okay, so moving on to the roadblocks that happened during our project development process. First is for this project development experience, we have a steep learning curve. For most of our group members, we only had the experience for school assignment based on a single computer science major subjects, and we realized the difference between computer science and software engineering. Second is we faced the real world's privacy issue and integration. So due to the constraints, we were unable to use the real APIs from Alexa. We had to use the mock API for implementing our projects. And that leads to there's not an actual product-wise user to give us feedbacks. So it's hard for the team to get benefits from agile methodologies. Last but not least, understanding the real world concept is hard for us too. It's hard for us because the experience we have is based on the school subjects, and understanding real industry context needing us to be more proactively communication. Next is our takeaways from this project development process. First is prioritizing tasks is very important. We practice Scrum in sizing and scoping each task into manageable units. It makes sure that we can tackle all the critical tasks first, managing time effectively, and also not to miss any deadlines. Second is we need to have the mentality of being patient. During the project development process, it's very natural that we have a conflict in scheduling because students have our school schedule and our sponsors have their work schedules. And understanding everyone has their own priorities and just be more patient, not only in learning new tech skills, but also like solving puzzles for development, can cultivating a more supportive working environment. Last but not least is not to be afraid to ask questions. So as I mentioned before, so for the there exist many technical terms that none of us have ever heard before. The best and quickest way to solve it is to asking questions as soon as possible. And a big thank to our sponsors, Raman and Henry, who have been very nice to us throughout the whole capstone year and also providing us very helpful and professional feedbacks for us to improve. A quick summary to what we deliver for the capstone project is that we deliver a user-friendly content moderation web application, which allows the Alexa users to modify their content on themselves. We also provide a detailed documentations on design and architectures. After we hand off the project to Amazon side, some integration that they may have is they could expand the modalities to accept images or other type of input. And then they could also implement the real APIs for the projects to have the real functionality to be able to work. Thank you for watching, and now we're open for any questions you have.
First, I'd like to say the demo was great. You guys need to give me a tutorial so I can improve on my presentation at work. My question is, on the authentication part, when does that take place?
So like users have to be authenticated even before they log in. So like before you see the homepage, you have to be authenticated first in order to use our application.
Okay, thank you.
Other questions for the team?
Great presentation, guys. I just want to ask, is the locale automatically detected, or is that something you input first and then you upload the file or the manual input?
Since we're in the US, we chose like US as our default locale, but like users can change the locale if we were to like expand other if we were to expand into like other regions.
Okay, that was my question. Thank you.
First, I'd just like to say, great project, guys. You've done an amazing amount of work here and a lot of functionality. In your system, being able to handle files is always a risk in these types of applications because the formatting of the file may end up causing problems in the back end. Is there any type of validation in your system to make sure that the files contain information in the appropriate format for the underlying systems?
Yeah, actually, we did a lot of validation for all the files that we accept. So we accept CSV, Excel, and JSON. So like we have validation for each, and for the CSV, since like we expect people to like have commas when they speak or like maybe use commas in their testing, we made it so that the delimiter is like double commas to ensure that the safety of our application. And there's also a notification that pops up when not all the requirements are met to like show you the actual like requirements.
All right, let's thank the team. Thank you.
For Zoom, I just need to share screen, correct?
You don't need to be logged into Zoom.
Can you check if the clicker works? Could you click through just to? Perfect. Howdy, y'all. Thank you for joining us here on Projects Day. We're Team 2402. My name's Daniel Violil. I'm joined by Carmel Laurentia, Koa Nguyen, Ihor Sherstwick, and Julian Warren. Without further ado, let's jump into the background. So we collaborated with the Amazon ASCII team, as you heard before, the Amazon Sensitive Content Intelligence team. They're primarily focused on catching, monitoring, in trust-busting interactions with Amazon, catching those early and making sure that we can detect those, as well as ensuring that better interactions are occurring going forward. That being said, I can pass it on to Julian to talk a little bit more on the initial problem statement.
Great. So Amazon collects customer feedback through 7 different channels, and one of these channels is social media. This channel is getting more and more popular among users, but it's unfortunately also super hard to monitor because there's just so many different sites, and often users just post their feedback without even tagging Amazon or Alexa. And in recent years, there were a couple of incidences where severe issues went undetected for too long on Reddit. There were even some Amazon employees that started monitoring themselves Reddit in their morning routine, just scrolling through Reddit and finding severe issues. And that's obviously not efficient or comprehensive. And this is where our project comes into play, because we build a system that collects customer feedback from multiple subreddits, analyzes them through a couple of machine learning models, and then displays the results in a single web page. And on that web page, the Amazon employee can basically see the recent trends in keywords that appeared very often, or topics that were talked about very often. The posts are also sorted by sentiment, and you can also find the posts that were the most viral, so that received the most attention through comments or upvotes. Yeah, this is a very, very proactive approach and hopefully more comprehensive and efficient for Amazon. And Carmel will show you the UI itself.
So this is the dashboard that we made to showcase the posts that we have collected and analyzed. So for this dashboard, we utilize AWS Amplify to connect the backend into our front-end React app, and also used S3 bucket, which is also a AWS service, to minimize the frequency of data fetching. In this dashboard, there are two main parts. The first part is the word cloud to provide an overview of the keywords and how many times it occurs. And then the second part is the trends, focusing specifically on negative sentiment posts. So this is the first interactive tabs in the trend section, which show you the topics and the frequency, listing the most frequent one on the top. And then the second tab is the top 10 keywords, and in the same way as the top 5 keywords is also listed the keywords and its frequency. And then if you click on one of the item, it will display you an expanded view of the post that is related to that item. And then furthermore, if you click on one of the item, it will display a pop-up window to show the detail of the post, including the post content, our analysis result, and the link to the post itself. And then for our third interactive tabs is our viral posts, to highlight the posts that have the most user engagement, determined by the sum of the number of comments and number of upvotes. This is useful for Amazon to determine which posts and which topic have the most user attention and might need attention from Amazon. So in this last interactive tabs is the most important part in our dashboard, as user can freely browse all the posts, and they can also filter and sort the result. And now we're moving on to architecture by Ihor.
Right, I'm going to give you guys some context. So our project is built on Amazon cloud infrastructure, and we use a number of different AWS cloud components. Our first one is AWS Lambda functions. The Lambda functions is the cloud compute service that allows us to run code based on different triggers. So this event-driven nature allows us to run our code based on various triggers and skips the need to manage servers. Next, we have the DynamoDB. DynamoDB is a NoSQL database service. We use it as our main service, and we store all the ready data as well as all the analysis data there. Its NoSQL nature allows us to work with unstructured data efficiently. Next, the Amazon S3 is the object storage service. Its primary use is its primary use is as a cache for our front-end service. Next, Amazon Comprehend, which is natural language processing service that allows us to analyze text, to extract sentiment, keywords, and other insights. Next, let's move on to the high overview of our project. So our project is a data processing pipeline that its main objective of which is to automate the collection, storage, and analysis of the feedback from Reddit. First step of the pipeline is the crawler. The main objective here is to automate the collection of posts from different subreddits to ensure the continuous data inflow. Next, we have the data analysis. There are two steps. First is the AWS Comprehend. We use AWS Comprehend to extract sentiment, keywords, and toxicity. Next, we have the topic detection model that we trained ourselves that allows us to highlight any points of interest about the post to Amazon. Last but not least, the UI, which is a crucial part of the project that enables users to interact with the data. The UI is powered by the Trend API. Next, let's look at the detail overview of the system. We used two different Lambda functions for the crawler. First one is the subreddit crawler, which basically runs every hour and collects all the posts available at Reddit. Its main objective is to collect as much data as possible, so we get all the recent feedback promptly. Complementing this, we have the updating crawler, which runs daily and checks all the posts within this 3-day window that we already have to see if there is any new content, like new comments, new upvotes, or anything like that. We have our Reddit post database, which is just used to store all the data that comes from crawlers. We have analyzed post database, which is used to store post data and analysis data that comes from comprehend and topic analysis. S3 cache, again, is used to power our front end. And we also have the Trend API, which allows a secure and structured way to access the data and powers our front end. So all of these components work seamlessly together to automate the collection, storage, and analysis of feedback on Amazon products. Next, I'm going to pass it on to Julian to talk about our models.
Great. So after our pipeline was up and running, we wanted to see how good our models perform and maybe if we could even improve them. And for that, we did some fine-tuning for text classification models, once for topic and once for sentiment classification. For topic classification, we fine-tuned one model with training data that was automatically labeled through a topic modeling job. And the other model was trained, fine-tuned with manually labeled data, which was a couple less posts, obviously, because we couldn't do as many. But as you see in the graphic, the model fine-tuned with manually labeled data actually performed better and is now utilized in our pipeline. For sentiment, we again fine-tuned two models, this time both with manually labeled data, but the difference lies in the number of classes it classifies in. Basically, the first one has 4 classes: positive, negative, mixed, and neutral. The second one that we fine-tuned only positive and negative. And we compared both of those to the stock version that you get from AWS Comprehend Sentiment Analysis, which is here in gray. And that one performed best for our use case and is now utilized in our pipeline. So now Ko will tell you more about testing.
All right, thank you, Julian. So now with everything in place, we need to have something to make sure that the system works as expected, which is why we have testing. And there are 2 types of tests. One is the unit test, and the second is the user interface test. With the unit test, we have 2 main goals. One is to verify that each component and each method, they work as expected. And second is all edge cases that would cause wrong results or even cause the system to fail are taken care of. For example, with the subreddit crawler, we make sure that it stays within the access rate limit, and in the system, it can transfer the collected data from Reddit to databases for storage. And if it has any problem, it will not cause the entire system to fail. And next is the user interface test. Usually, when we have a user interface or make changes to one, we want to actually use it to see if there's any error or unexpected behavior. And the process of going through all the links, buttons, drop-downs, etc. is very repetitive, time-consuming, and can even be costly if we hire someone to do so. Because of that, we developed this test to automate the process of manually testing the UI. The test will also help us identify changes that cause the previously approved version of the UI to break just by looking at the log of the test. As you can see on the right, it has all the steps. Moving on, I will present to you about challenges that we faced and how we overcame them. For the Reddit API, it might return unusable data every now and then. And because we are using the free tier version, we only have 100 accesses per minute, which is not enough given the end goal of this project is to monitor the customer feedback on the entire social media. And the solutions are to check for all data that came from Reddit for their usability and create multiple crawlers to make up for the lack of access rate. And next are the challenges and the solution for the machine learning model. All of them used in this project are free and censored. Because of that, we cannot process sensitive data. Also, due to very limited time to do manual data labeling, no publicly available data set, and very limited AWS credit, we virtually didn't have enough resources to fine-tune our models. And the solutions are to create our own data set. And the results are 2 models, which are the topic classification model and a sentiment classification model. By overcoming those challenges, we're able to keep up with customer feedback and process data faster and more efficient. And now I'll pass to Danny to talk about future ideas.
Yeah, thanks, Scott. Yeah, working on this project was a dream, and it was great getting the experience to, correspond with ASCII team as well as just working on new skills that we wouldn't have touched on otherwise. Going forward, if we were to continue development on this project, we would have wanted to expand our crawler so that it would work on non-Reddit data, as well as kind of goes in point. Reddit data is primarily only English content, at least for r/Alexa and r/Fire TV. Were we to try and include subreddits that were non-English, we'd have to expand our crawler to be able to handle that, as well as, yes, trying to deal with other social media platforms, Twitter, Instagram, Facebook, stuff like that. We'd need to include our image analysis in our model, but that would be great to work on going forward. Another point that we'd like to touch on was expanding model training. We were only able to work on model training during that last second quarter, and so being able to expand training, whether it was allowing more time, expanding more different model use that we could add on to our suite of models that we used for testing and analysis, as well as, adding more data, frankly. Using only 1,000 posts, you can only attain so much recall and precision, and so having more time to be able to acquire more data would have meant better recall and precision going forward. That being said, again, we want to give a great thanks to those that made this project possible. Those at Amazon specifically, our project manager, Sundar Chandrasekharan, as well as those at SU that made this project possible in the first place. We'd be remiss to not mention Professor Beatrice Diaz-Acosta for invaluable input throughout the project and development. That being said, thank you for your time. Any questions?
Great presentation, guys. One question I wanted to ask you guys was there a reason you guys specifically chose Reddit as your first social media app to run your program on?
Yes, so going back to the problem statement, so there was in 2021, there was a case when a boy asked Alexa for a challenge, and Alexa told him to put 2 pins in a plug. So that's endangering the customer, and someone posted about this on Reddit, and it went viral, and Amazon didn't see it until 3 days later. So it caused reputable damages to Amazon, and that's why the idea for this project emerged, and that's why the employees started monitoring Reddit on a daily basis. So that's why we chose Reddit as our first step.
Thank you.
I hadn't really heard of Comprehend before. A couple questions about it. Is it familiar with all of the abbreviations that typically appear in social media, like IMHO and WTF and stuff like that? And the second question is it good enough to recognize sarcasm? Because people do that a lot sometimes. They'll say something which is not what they mean, but people understand it.
Juliet, you want to go?
Yeah, so Comprehend is basically just a service from AWS itself that gives you all these machine learning models. I would assume that it is trained on such a large data set that already incorporates these abbreviations, but it's obviously not the focus of it. The same thing is for sarcasm. It does not have a functionality to filter out sarcasm specifically. It usually only does sentiment, toxicity, and keywords. Yeah.
I can also touch on, or just add on that I think that was also part of the impetus behind trying to train our own model was because we were able to by hand read some of those posts, we were able to ourselves determine intent in that and incorporate that into the final product.
We have time for one more question. Any questions on Zoom? No. Okay. Sure.
So, so that's also another reason that we used Reddit. These social media sites often have APIs, basically functions that they provide us developers that we can call to get data from their sites, and they're sometimes free, or in our case, they're at least limited. That's why we only have 100 requests per minute, for example. Yeah. So, and to the other part, everything that is on Reddit is public data. So technically, we're not doing anything that requires moderation, yet there are concerns that in the future, if somebody posts their banking number or whatever, they shouldn't do it. That would be something that we would need to take into consideration, obviously. But technically, it's the user's choice to post what he wants. There's nothing else that we get from the account, from the Reddit account, from the user. It's just what they said.
So for the Reddit, it's free version, but it's still safe because like if Reddit ordered us to take down data, if all of them, we have to follow that rules. If not, we will get sued. Also for the machine learning model that we use in this project, it has a feature that will mask away your privacy. Like, for example, like, all your personal info, like your credit card number, your name, your social security number. We can potentially implement that in the future if we have a chance, but for now, we are not focusing on that yet. So I just want to make sure that you know that.
All right. Thank you, team. And this... So this is the end of session 2. And if you have any questions for the 3 teams that presented in this session, please find them at their posters at 4:15. And the next session begins at 3:15. So, thank you.
Welcome to Project Day. Students in engineering, computer science, and environmental science have worked throughout the year on challenging real-world projects from external partners. The students applied technical knowledge from coursework and gained skills in project management, teamwork, budgeting, technical writing, and oral communications. Project Day is the culmination of their experience.
Seattle University and the Project Center and the way that they like to tie in projects from industry into their senior design projects, I think is really excellent.
They can learn from the professionals and the experience while they're in school.
The professionalism of the engineering staff, the willingness to mentor students that are within a university environment still, bring them into more of a career-driven
Mic check. Mic check.
Yes, it's low.
Testing? Testing? Hello? Okay.
Hello, everybody. Hello, and welcome to the third session of today's Project Day presentations. We have two presentations scheduled for this session, and the first presentation will be jointly delivered by two teams, the ECE and the ME teams, sponsored by AWS. And our second presentation will be by a team sponsored by SoundSense. So a few reminders before we get started. There will be time for questions and answers at the end of each presentation. So if you have a question, please raise your hand and I'll bring the mic over to you. For guests joining us via Zoom, just type your question in the chat window and we'll get to them. Thank you so much, and I'll hand it over to the first team.
Hello, everyone. We are teams ECE 24.1 and ME 24.1, and our project title is the AWS Availability Rover, sponsored by AWS. I know we're in the third session, so I know everyone's eager to go back to the poster session, but we do have about half an hour for our presentation today because it's to combine two teams, and as you can see, we have a lot of people up here. So please relax, sit back, get your popcorn, silence your cell phones, and just be ready for this long presentation we have. Thank you.
All right, starting with the introduction, my name is Abdullah. We have Benjamin, Brandon, and Lee, and we're the ECE team.
Hi everyone, my name is Parth, and here we have Bina, Tony, Justin, and David, and we're the ME team.
Next for the advisor and faculty, we have Dr. Singh and Dr. Dedfarnia as our faculty advisor. And also we have Derek, Chris, and Mike as our sponsor liaisons.
So to start off our presentation, we have three main sections that we'll be taking you through. The first will be the project overview, so the project statement that we had to solve, the requirements set for us by our project liaisons, as well as our initial design to solve said solution. Then we'll take you into the two main sections. The sensor overview will deal with the ECE side of things, such as what the sensors do and how they were set up. And then we'll go into the mechanical side of things, which will deal with frame design, wheels, as well as wire management. And then at the end, we'll do a quick recap with the conclusion of what we were able to complete in this project.
And starting off with the sponsor introduction, we have AWS, also known as Amazon Web Services, is a well-known cloud computing platform. It has over 100 data centers around the world, and also it's known for its scalability, reliability, and availability. And also it could offer cloud computing services, database management, storage options, and more.
Yeah, and this leads me to the main problem of this project, which is that currently there is no efficient way to measure server health or surrounding sensory data with 100% uptime. An example where this can be an issue is when there's a malfunction within a server rack, and if that malfunction is not accounted for quickly, it can lead to a further chain of issues leading to potential outages. Another issue is that server technicians currently have to work in harsh environments such as hot summers or cold winters. The ultimate end goal of this project through the years is for this cart to be autonomous, which would remove the server technician from these harsh environments. So the solution to this is a modular sensory platform which can be moved through a data center while measuring data from multiple sensors simultaneously. This is the Amazon Availability Rover.
The AWS Availability Rover is currently in its third iteration. The first iteration introduced the initial design with a lot of the sensors based off of a Rubbermaid cart. The second iteration improved on the design with aluminum T-slots and a linear actuator to allow it to fit through doors and reach higher on the server racks. And over the past year, we've been working on the third iteration.
So for the project scope for this year, the ECE team was tasked with revising and maintaining a lot of the previous year's systems, as a lot of them remained incomplete or needed some fixing to do. While we were at the data center and while we were on the site visit, the data center technicians actually requested us to determine maximum temperature outputs from the thermal captures that were able to be taken from previous years, but there wasn't any data being given from them. So they asked us on site to give us maximum temperature outputs. Something else that we were something we were also asked to do were to improve the user interface, as previously the user interface was implemented through command line. If you know anything about command line, it's all text. And so it was supposed to be more intuitive, more visual for a data center technician to pick up and learn. We were also asked to improve autonomy for this year. So autonomy through linear actuators. The linear actuator and thermal camera system now has a 21-step function where it will automatically go through all 21 steps and take the thermal pictures at each step. As well as with the LiDAR sensor, we are taking steps towards autonomy by creating an offline 2D map with the LiDAR sensor. Lastly, we were asked to improve the barcode system, as the barcode system previously was not finished, and this year we have uprooted it and redone it, and now is completely finished on our end.
The ME team was tasked with reducing complexity, weight, implementing
wire management and protecting the components. Our goals for these were to get the weight at or below 100 pounds, make sure that assembly and disassembly are toolless, ensure that zero components are exposed to the environment, and improve wire management through quick connectors and drag chains.
So I'll be explaining the functional flowchart of how all the sensors are connected to the laptop. So first off, we have the camera barcode system, which is connected to the laptop via micro USB. Next up, after that, we have the button interface, which controls the linear actuator. And the linear actuator is connected to a network switch, which will send data through an Ethernet cable. Likewise, next we have the thermal camera, which is also connected via Ethernet cable to the network switch and sends data about thermal images. Following the timeline, we have LiDAR, which is also connected via micro USB to the laptop. And we have two microcontrollers on the cart, which is also known as the STM32. We have the cart and the platform STM32. The cart STM32 collects data of ultrasonic microphones, ambient sensors, and this is connected via USB-C to the laptop. And we have the platform STM32, which is collecting microphone data on the platform and is connected via USB-C.
All right, so for the first sensor that we'll be talking about, the camera barcode scanning. So with a lot of data being taken from these data centers, there needs to be identification of said data to know where it's from, and that's where the system comes in place. This will be used to scan 2x3 or 2x6 inch barcodes that are on the floor to identify the server racks. And so how does it work, right? So first you have to take a picture. So we use a Nikon D3500 DSLR camera, which will take a photo. And after we take said photo, we'll apply some pre-processing to prep it for the model to be able to decode the barcodes that are in that image. Once we do that, so it'll decode three types of main barcodes, UPC-A, code 128, and code 39. And those are the top three that are used at data centers. Then we'll take these values and store them in a MySQL database where they can be later linked to other data taken from other sensors. And then to meet AWS's security requirements, we'll appropriately deal with these photos. So in case the cart gets taken out of the data center, we want to then remove the photos from the cart and make sure that no images taken within the data center are taken out. And because we have multiple sensors running at the same, or multiple sensors that are taking in data, we want to make sure that the time is efficiently used. So anytime that we can parallelize different processes, we want to take that. So this is one of the systems that we use a thread to run in the background. So here's an example. Let's say you're a data center technician and you tell the UI to take a picture. So it'll remotely tell the camera to take a photo, which will then be sent to the raw directory. So this directory will be then taken with Python code and applied three different pre-processing techniques. The first is grayscaling, because barcode is black and white, so color is a disturbance and not needed. The next is Gaussian blur, and this removes noise and specks that you get from very far away photos, so it makes the lines more defined and easier to identify. And then the last one is brightness and contrast, and that's to make the blacks more easily distinguished from the whites. Once we do that, we pass it into the CV2 model, and there are two main outcomes. If it's a success, we can take the CV2 model will give us the barcode value as well as points of where the barcode is located, and we could take those points and store it on the image and give it to or send it to the UI for the data center technician to be able to view. But in the case that it is not taken and it is unable to scan, we put that in a separate directory so the data center technician knows that this barcode potentially will not be able to, is damaged or is unable to be scanned. So either or, they'll be sent to the UI where the data center technician can view it. So here's an example. Before I start the video, we have code 128 code with 437, 709, a bunch of other numbers you probably won't remember. So we start with this. So you drive right up and have it in front of the cart, and then you go to the UI where you have a bunch of buttons for each of the sections. Let's open a barcode, and we say, all right, we want to take capture. So it's not taken in the frame because of the video, but it takes a flash and then starts loading, and the loading bar will give a constant update on how far it is in that process I just showed you. And if we wait a couple of seconds, you can see that, yeah, it did work. 4377709, it shows the values and it shows the placement of the barcode.
All right, hi, I'm Lee, and I'll be talking about the user interface for this year. So for speaking terms, I'm just going to be referring to user interface as interface or UI, just for short. All these terms are interchangeable with each other. So for the user interface, previously it was using command line. Like I said about command line, it is all text, and it is very hard to decipher if you were to read from one of the points that, like it says, it asks for a corresponding choice. I said 3, and now I have all this data that I need to parse through. Very hard to read, not very intuitive to work with. And so this year we are upgrading and moving on to Python rather than command line. And so with Python, we're using the library PySimple-GUI. As its name says, is a simple look, is a simple use in code as well to be able to implement a user interface. And now this year, the user interface looks like this. They are clear buttons to press. There is clearly a way to move around the user interface, and if you know what you want to do. And if you don't know what you want to do, there's also a help button telling you what you can do with the user interface. And so, like Ben just showed you with the user interface, there's the barcode window. Here's the example again. And if you want to capture an image, you can take you can capture an image with anything related to barcode on this window, and it'll have the loading bar just to give progressive updates again. But you can also do the other functions that were requested, which is open the file location and also clear the cache. Opening the file location will open the location of where all the images are at, and clearing cache will delete all those images in that stored folder. And there are similar functions for these for both the thermal system and the LiDAR system, which you will see in the further demos later on.
Hi, I'm Brandon. I'm going to be explaining about linear actuators and thermal cameras. So right here you can see is the linear actuator located on the cart. As you can see, it moves up and down along with the drag chain. So I would like to mention that as you saw in the second iteration photo, there was 2 sets of linear actuators. We have reduced this to 1 due to Liaison's recommendations, just to keep it more simple. So it makes it easier to debug the motor controllers if there's any issues. And second off, I would like to say is that in the previous years, there's some jittering issues due to the joystick controller. So we have moved to a digital switch controller, as you can see on the image on the left. So the main goal of this year is going towards the steps of autonomy. So we're going to traverse, the platform on the linear actuator is going to traverse through the height of the server racks at pre-designed heights, which will capture data of temperature values along with decibel levels. So how the linear actuator functions is that there's a 3-button interface. The first button will move the linear actuator up and down. The second button is the toggle button up and down, and the third button is the automation button. So it would automatically set pre-designed heights at certain heights on the linear actuator. Then it will capture thermal data along with the temperature data as well. Here's the thermal camera located on the platform. So like what Lee mentioned, during the site visit during fall quarter, the data center technicians requested us to give out temperature values along with some type of readable image. So the main goal of this year is to provide PNG images. In the previous years, they provide IRB file types, which is just a proprietary file type, which is not accessible through program. And we're also supposed to give temperature values. And then we want to output those temperature values, the max temperature values, into the UI along with the PNG images. So the main function of the thermal camera is that once the picture is taken, it will go through the software and convert those images into a TXT file containing all the pixel values, along with converting all of it to PNG images. And as you can see on the right, it shows the image along with the max temperature values on the right. And this also uploads to the MySQL database along with the max temperature. Here's my demo for the thermal camera. This is through the UI. So I'm going to open up the file directory. As you can see, it contains all the files. Next up, we can view all the images. We can iterate through all the images. So it takes 23 images of all the server racks. As you can see, that's me in the photo. Shows the temperature. And then as requested as AWS, they wanted to clear the cache. So once I click clear cache, it'll delete everything in the directory. As you can see, it's all empty.
Hey, I'm Tony, and I'm going to talk about the drag chain. So with the use of linear actuators and thermal cameras and everything moving in the vertical plane, we're going to have to deal with vertically moving wires. And we must protect these vertically moving wires as well as guide them to ensure that they do not move outside of the frame of the cart. Because if it did, there's a chance that it could snag onto something, and that would not be good. So we decided to stick with drag chains. So Drag chains are good because one benefit of them is that we are able to change the length of the drag chains to adjust to varying lengths of wire. And the specific version we chose is the lay and snap version available on McMaster-Carr. And this version is good because it allows us to open the drag chains and directly lay the wires directly inside. If the drag chain links are not open, we cannot feed the wires through because the wire connector heads are too large and they do not fit in the drag chain itself. And we specifically chose the size of the drag chain based off of the outer diameters of the wires as well as the total maximum widths of the wires. So for our system, we are using 2 drag chains. We are using 2 drag chains because there are 2 varying heights that we must accommodate for. So there's the height of the linear actuator, and then there's the height of the moving sensor platform. And we also mounted these drag chains using 3D printed mounts. These mounts allow for direct attachment and easy disassembly for when you take the drag chain off the cart. And here's a video of the entire thing. So you can see the autonomous movement of the linear actuator and the thermal camera moving alongside it. And you can see the drag chain moving alongside the linear actuator and thermal camera as it's going up and down.
So we'll be moving on to environmental sensors. So the main goal of environmental sensors is to provide proper conversion rates. So the microphones in the previous years only provided voltages, so we want to convert those to decibel values. So it's better for regulations and understanding for the data center technicians to understand how loud the data center is. So the environmental sensors are made up of 4 systems: the ultrasonic microphone, the MAX 446 microphone. We have time of flight sensors. You can think of it as proximity sensors. And then we have the ambient sensor. So the main goal of the functionality of the environmental sensors is just to check the health of the servers. So we're collecting data about ambient temperature, pressure, humidity, and also decibel levels of the microphones from the cart ultrasonic and then the platform S microphone, sorry. And then we also are taking the distance of the cart and the server racks from the TFO sensors.
All right, now my name is Abdullah, and we're going to move on to the last sensor on the list, which is LiDAR. And for the people who don't know what LiDAR is basically LiDAR's light detection and ranging. And basically the LiDAR houses 2 sensors, which is a laser and an actual sensor that captures that laser. And the laser travels towards a distance, then hits its surface, then it bounces off that surface back to the sensor. And then the LiDAR actually, by itself, it detects the actual distance between the LiDAR and the surface. And that creates only 1 data point in a 2D plane, since we're using a 2D LiDAR. And also, the LiDAR is capable of producing 1,450 data points per rotation. So, implementing the LiDAR is one of the most essential components for AWS long-term goal for achieving a fully autonomous system. And one of the advantages of LiDAR is basically it creates a detailed 2D map with all these data points that I explained at the beginning. And also it has high accuracy and precision. And a nice story that we visit a data center for the AWS. We tested our cart there, and essentially one of the sponsors, his name is Derek, he came up to us and he wanted to test the LiDAR's capability. So he held a book and he held a smaller item in front of the book and held it on the LiDAR. And to his surprise, actually, the LiDAR successfully detected the 2 different items and the 2 different depths as well, which shows the accuracy and precision for it. And also, lastly, we have LiDAR's advantage for operating offline. For security reasons that AWS requested. And finally, we have future recommendations. Since this is our 3rd year, we're planning to actually shift this to the next year and make it actually more of an essential component since it's a stretch goal. And also the other point that complements it is lack of motorized wheels. Since we don't have an automatic wheel, we cannot actually make it a fully autonomous system, so it's technically at the moment it's a semi-autonomous system. Moving on to the LiDAR demo, we click on the LiDAR button. It opens the 2D UI for the LiDAR, and that's the 2D plane. And when you click on scan, you can see these blue lines. These contain these individual points, data points. And also you can see the distance on the top left by moving the mouse, and also the angle of that surface. And also I did the similar test to Derek, our sponsor. I just put my hand up top and just move my finger and to see if it detects my fingers. And it's actually pretty successful. And that's just the basics of LiDAR, and there's a lot of potential for future innovation.
All right, hi, I'm Justin, and now I'll be moving into the mechanical section, starting with the frame design. Here you can see the frame that we redesigned for this year. And we'll move into the design goals. Our goals for the frame, just to remind you, were to reduce the complexity, reduce the weight, and add toolless assembly and disassembly. And our design requirements were to maintain the rigidity of the previous year's frame while enabling all the sensors to function properly. Here you can see our workflow for designing the frame. We went through ideation and then did some revisions. Key emphasis on the analysis section of weight calculation and finite element analysis before moving into design review. So here you can see some of the early ideations that we went through designing the frame. We chose 2 to make revisions on before finally moving on to the final chosen design. Both of those 2 that we've revised had accommodations for the toolless assembly in a very similar way, which you'll see later. So toolless assembly, we chose cam levers to attach at major junctions. There's 9 major junctions where you basically cam the lever over, so you twist it 90 degrees, and that'll release the tension, and you add tension by twisting it back another 90 degrees, and that tensions the junction. We chose these because they are cheap and easy to use off-the-shelf components, and we were able to securely attach each junction with only one, so we added several more to increase security. Here you can see the 4-part design of the frame. It's got 3 major sections, the linear actuator, upper and lower platforms, with vertical beams connecting the upper and lower platforms. These are the points where those cam lever junctions are present. The weight calculations we went through, we basically tallied up the lengths of the beams and calculated the weight. And the year 2 cart we found was over 47 pounds. The year 3 design that we proposed was 38 pounds, and the final year 3 design that we reached was 41 pounds. So we did successfully achieve our goal of reducing the weight of the frame. However, it wasn't as much as we predicted. That's because we needed to use some wider pieces of aluminum to accommodate for the wheels, which Parth will detail later. So a little background about finite element analysis. This is the analysis that we use to measure the deflection of the proposed frame and compare it to the existing frame to see if it would be suitably rigid. Finite element analysis solves equations by approximating over small distances, known as a mesh, and it uses this mesh to sum up the distances over the full equation, so you can use it to find stresses, and in this case we found deflection. We had 2 goals with this analysis. It was to determine the rigidity compared to the first year for suitability, and we wanted to choose the correct cross-sectional size because we were debating between 1.5 inch, which we chose, and 1 inch, which was proposed. So here you can see on the left, we have the model of the year 2 frame. That was the one that we were trying to mimic its strength of. And on the right, you can see the proposed frame, which we ended up choosing. We brought the cross-sections in from McMaster Carr, so we were able to use their actual data from the cross-sectional properties from their manufacturer. In blue, you can see those are points of minimum deflection, and in red is the points of the most deflection. These pictures are dramatically emphasized, so you wouldn't actually see this much deflection on the rover, but it's a good visualization tool. So tabulating these results, you can see that we accounted for mesh size, which can affect some of the outcomes based on how large your approximations you're taking are. But for these equations, we didn't find any difference in the mesh size because you could theoretically find them by hand, except it would be a lot more complicated and take a lot longer. You can see that they are both on the same order of magnitude, which is how we know that the frame is going to be significantly rigid or approximately the same rigidity compared to the last year. We didn't see any drastic increases in deflection with the proposed design, so we felt comfortable to go ahead with it. We chose the 1.5 inch design because it showed this similar rigidity, whereas the 1 inch design had approximately 10 times the deflection of both the year 2 and the 1.5 inch design.
Hi everyone, my name is Parth and I'll be talking to you about wheels. So when we made our first initial visit in the fall to the data center, we noticed that the floors were very rough concrete and there was a lot of cracks and crevices in between each of the panels on the floor. And so we wanted to explore a better wheel option in order for the cart to be able to be moved easily, not only for the server technician, just as a whole. So last year they had 3-inch rubber wheels, and this year we wanted to explore 2 different properties to change, which were the material and the polyurethane, or rubber and polyurethane. As you can see, the 2 materials we chose are rubber and polyurethane, and the 2 diameters we chose are 3 inches and 6 inches. What we used to evaluate these 2 materials and diameters was rolling resistance. So what rolling resistance is, it's the resistance that needs to be overcome between the floor and the wheel in order for the cart to move. And as you can see, between the 3-inch and the 6-inch, the rolling resistance is cut in half for both the materials. And between the 2 materials, rubber and polyurethane, polyurethane has half as much rolling resistance as rubber. From this, we can state that increasing the diameter is a clear-cut option. But for material, we want to explore further properties to see if there's anything else that we could look for. So for rubbers, what rubber does is it provides better cushioning and resilience. It's cheaper and it's quieter, but it wears easily and has a higher rolling resistance, as previously stated. For polyurethane, it has a higher load capacity, a lower roll resistance, and it's more durable, almost 3 times as more durable as rubber, but it's more expensive and has bumpier rides. So we presented this data to our sponsors and we got some advice back. They stated that they wanted something that was more durable, and a quote from one of our sponsors, Mike, states that he didn't want the technician to move around a sandbag, as the data racks in between the server are very short space, so the cart from making frequent start and stops. This makes the rolling resistance that much more crucial. So with that, we chose the 6-inch polyurethane wheels. We have 2 fixed casters and 2 swivel casters. And the swivel casters are mounted horizontally on a double rail, as Justin previously mentioned. So the next issue we faced was, or I guess problem we faced, was where to put the swivel wheels. They could either be put at the front of the cart or at the back of the cart, nearest to where the server technician is pushing. So with further research, from a quote from Darker Caster states that the swivel wheels are best put nearest to the load, where the load is being put. So this would mean that the swivel wheels are placed at the back of the cart, making it easy for the technician to turn the cart around the corners easier, as the data center gaps are very narrow in the data center.
Hi, my name is Bina, and I'll be talking about the general wire management. So just to reiterate on the design goal, we wanted to obviously implement wire management, but it's also to help reduce the complexity when we're disassembling and assembling the cart. The requirement is to make sure that we protect the wires, we provide organization, and we also implement quick connectors. So we first started out with a list of components. Obviously, we talked about the list of components with the EC team previously. So this is a list that we built with them from all the things that they were using, but we needed to map out where they would be on our frame design. So we had thoughts to either put them on the top platform or the bottom platform, which is where most of the components would be. And so after deciding with the ECE team where everything would go, this is what we started out with initially. So this is our frame design as you saw previously. So as Justin said, we are splitting our frame up into 3 main parts. We have the top platform, the bottom platform, and the linear actuator. So initially, our plan was to use bundles of wires that would go with each of these main 3 components when they're split up. We would use nylon cable sleeves to create 3 neat bundles. However, we had a problem, as you can see in the image. Although we had 3 clean bundles at the exit points, all those wires in each of those bundles went to many different locations. 3 of those bundles together had 15 to 20 different plugs that we needed to take apart. They went to the power strip, the battery, the network box, and there was also the terminal rail. So that was a problem. It didn't help with our disassembly process. So to fix that, we implemented an undermounted cable net. and that is mounted to the the top underside of the top platform. So that now holds basically everything you saw previously, all the power bricks, the network box, the power strip. It also helps because we're pushing the cart. So if you hit a bump in the server room or just when you're pushing it into the building, previously everything could fall off the cart. Now with the cable net, that's not going to happen. We still use the nylon cable sleeves like we mentioned earlier, but that's only to protect any like loose, thin wires that need extra protection. Mainly those were used when outside of the net. So now with the 15 to 20 plugs we had previously, that is now just 2 plugs and they come from the battery. So you're now just unplugging the power strip and the 12-volt power rail wire. So another thing was quick connectors. As Justin mentioned previously, we are splitting our frame up, so it's not just one thing anymore. To help with the complexity reduction in disassembly and assembly, we implemented quick connectors. So the quick connectors that we used were automotive electrical wire quick connectors. They were used because they were easy to implement. They were also very cheap. And then we also found that they added extra waterproof and dustproof, which we weren't looking for, but it was nice to have. So an example. So this is our cart. So examples of where these quick connectors are implemented are junctions where we wanted our frame to be or where we had our frame disassembled. So as you can see in the corner, our top frame is disassembled or separated with the vertical bar. So that's where one of the junctions would be and where some of our quick connectors are. Another is where the drag chain and linear actuator connect. So previously, we talked about removing the linear actuator from the main assembly. Well, the linear actuator also has the drag chain attached to that. And so to protect the drag chain from damage, we also need to add a quick connector to disconnect that from the linear actuator assembly to protect it.
Hi, I'm David. I'll be going over the second portion of wire management, which is component protection. Our objectives for these were to secure the components to the frame, protect them from physical threats, and ensure compatibility with the quick connectors. As Bina mentioned, quick connectors are important to our project for both ease of assembling and disassembling. We were fortunate enough to inherit the housings from previous teams, such as the Hall effect sensors and the TOF sensors. We did, however, have to buy some new housings and mounts, such as for the Nikon that Ben talked about earlier and for the Raspberry Pi.
So with a system with many different components, we have to have a lot of integration testing, and that's what we get into with this section. So we had 2 main testing phases. We had the on-campus testing, which was in our projects room, and then we had an on-site testing, which was at a test data center, AWS test data center. So the main things that we got from our on-site testing, that was pretty much making sure that the sensors worked as we could, or the best that we could here, making sure that any data that was recorded was stored into the tables correctly. And so we got that the barcode camera system was able to decode barcodes correctly for most of the time and store these values into the SQL table all the time. We also made sure that the environmental sensors were continuously pulling data of the environment and storing that as well seamlessly. And then we made sure that the captured thermal images and linear actuators were working, that the captured images could get the values extracted from them, and that those images are able to be viewable. And then that LiDAR actually maps the 2D environment, so we went into different environments in our projects room to make sure that it accurately reflected changes that happened in the surrounding. And then the last thing is having a UI that was able to be worked with and connected to all the sensors, which we checked to make sure that the data center technician had easy time using this solution and system. Once we went on site, we learned a couple of issues that we had to take care of. So the first was that the barcode camera system suffers in terms of that if the barcode is damaged heavily, that it won't be able to scan. And so, as said before, there's a system now in place to separate those barcodes and tell the data center technician that they need to be replaced. The second thing is that there were some motor movements, such as stuttering with a linear actuator that was discovered, but that issue was resolved in the last week. Then the final thing that we had to fix was that UI needed bigger text, and this was to make it that the data center technician can easily just read the screen quickly and continue his work without having to look very close to the screen to see the small text. And one of the good things we found when testing was that we wanted to make sure our solution worked for a whole workday, so 8 hours. And after testing, we found that on battery power, with all the motors working and sensors working simultaneously, it only took 6% of battery away in 1 hour.
As stated before, weight reduction was one of the main goals we had as a team. And specifically, we were supposed to get it below 100 pounds. And comparing to year two's rover, some of the weight reduction was done from the frame by reducing the amount of T-slot we used, but the majority of the weight lost was through the removal of a set of linear actuators. And because of that removal, we were able to remove about 30 pounds from the overall rover, and we were successful in reducing the rover under 100 pounds.
We did test assembly and disassembly at the data center and on campus. Disassembly and assembly could be done with 1 to 2 people. And as you can see below, it took a maximum of 5 to 10 minutes to assemble and 25 to 30 minutes to disassemble. Next. Assembly and disassembly can easily be done with, or more easily done with 4 or more people, as we did at the data centers shown in the picture here, taking us less than 15 minutes while there to assemble.
So for the final part, just to wrap up what we covered. So as Lee and Partha had talked about, the deliverables that we were supposed to meet, so let's just go through them. So first, temperature value. We were able to do that with the thermal imaging. The images are able to be taken and the value is able to be extracted. Improved UI, it switched from command line interface to an actual GUI that they can open and click buttons easily. Autonomy, linear actuators have a script that can now go to all 20 heights of a server and take pictures without the data center technician needing to manually move. And our stretch goal, which was LiDAR, is implemented as a tool for later years goal of autonomy. And our barcode reader is able to reliably scan barcodes. And then that's it for the EC section. Now if we move on to the mechanical engineering goals, weight reduction, as stated before, has been met. Complexity reduction has been met with the toolless design of disassembly and assembly of the cart. Component protection, making sure that if the card is hit if the data center actually hits the card into a server, that the components will still be able to work and are protected. That has been done. And lastly, for easy assembly, disassembly, and wire management, that has also been completed. These are all the deliverables that have been requested by us, and we have been able to meet all of them. So here are our references. Any questions?
Thank you. There are several questions on Zoom. The first one is a 2-part, and yes, I'll let you arrange how to. The first one has 2 parts. Does the cart have a gyroscope to allow it to change direction horizontally and notify the user if it's off balance? Can the barcode scanner scan QR codes?
So there's not a gyroscope for tilting, as that wasn't one of the deliverables that we had. And then as for the camera barcode scanning, currently it can. It has the potential to scan for QR codes, as CV2 does have that capability, but it is not currently integrated. Those 3 main barcode encoding types were the ones that are focused.
We have time for one more question, just one. Okay.
I have a question for the wheels team. I was wondering if you guys looked into Omni wheels or swerve drives, because I believe they could probably provide like a greater range of motion compared to the wheels that you guys are currently using.
Yeah, are you talking about wheels that? Yeah, are you talking about wheels that can be moved in all 4 directions?
Yes.
Yeah, we did look into that. I think for now, what we wanted was basically wheels that could control around tight corners, and then the next step, as we move towards autonomy, the next step for the wheels is actually motorized wheels.
Mm-hmm.
So that team will look into the motorized wheels next.
Thank you, team. And if you'd like to take a closer look at their prototype, please visit them during the poster session at 4:15. Thank you.
Take it out.
Let me go.
Yeah.
Testing.
Red is on.
Hi everyone, we're Team ECE 24.4 and today we're going to be talking to you about our noise sensitivity prototype. This is our team.
Hello everyone, my name is Jonah Casinas. I'm majoring in electrical engineering.
My name is Kyle Fukutami. I'm also majoring in electrical engineering.
My name is Maximilian Hofbauer, and I'm majoring in computer engineering.
My name is Alexandra Molina and I'm also majoring in computer engineering. Our faculty advisor is Mara Nelson and our liaison engineer is Dr. Bunny Schneider. For this project, we work with the company SoundSense, and SoundSense is a WBE, or a woman business enterprise, consulting and engineering company with over 30 years of experience. They specialize in architectural room acoustics, noise and vibration control, as well as sound separation or isolation.
To best cover the work we did this quarter, we must first acknowledge that as the team worked on the patent-pending prototype, we are working under the proprietary techniques and methods. So I can't quite disclose everything about our project today in this session, but we're going to skirt around that as best as we can. In their research, SoundSense found a noise set that when people displayed a sensitivity to could indicate the presence of certain diseases. We can think about this in our normal life as humans having a base response to sound. You can think of that when you hear a loud noise, how your muscles might tense, your heart rate might increase, just as something unnerving like a glass breaking or twig breaking might do the same thing. So our sponsor asked if we could transition their research into quantifying these responses through bioelectric signals to aid in their research to help identify and diagnose health conditions through sound.
So as sort of an introduction to our project, our entire project scope was to basically build a test system that is created around the previously mentioned proprietary research that Max just talked about. And so the test system, in essence, will be able to play an audio sample to the subject in order to stimulate some kind of response, and then we will simultaneously measure that response through their vital signs and other bioelectric signals. And what this will essentially allow us to do is to perform a quick diagnostic check, checking for certain health conditions early on in the diagnostic process. So going a little bit more into detail, we have our test system overview, and this slide covers a majority of the hardware that our test system uses. So first, we use just standard sensor cables and patches, allowing the system to input data from the user. And so this is what actually connects to the subject and is able to collect the bioelectric signals. And this is able to collect bioelectric signals such as ECG, EDA, and EMG. Next, we have a vital sign simulator, and this was mainly used for testing. And what this allowed us to do was sort of mimic the sort of bioelectric responses that you would get from a real-life patient. Next, we have our Bitalino Revolutions biosignals platform, which is just a printed circuit board that allows us to collect and import the bioelectric signals from the subject and to be saved and graphed later on in the testing sequence. Our test system was built to be ran on a Windows computer, and so we will be using a Windows computer with the test system program running in the background. And lastly, we have our noise isolating headphones, and this is to ensure that no external noises are is going to interrupt while the test sequence is running.
So in terms of the subject testing process, there's a couple things we have to go over. So first being the collection of preliminary data. So this would be the user data. So it would be name, a reference number we may give them, and other things that would help pull their name later in their data. Another thing is the baseline vitals and bioelectric signals. And this is what we're going to be testing for. So ECG, EDA, and EMG. Finally, the baseline hearing response, which is a below audible hearing level that we will establish with our test. And then we are going to initiate and run our audio test procedure, and that will play the generated audio to the user and record the user's vital signs and bioelectric signals. And then while this is happening, it will detect any events that occur. And finally, it will output the visual summary of the data, which will come in the form of graphs. So for the customer needs of our test system, there's a couple things that are here. So first thing being, the system must possess a high degree of portability and ease of use. The reason this is important is that this is supposed to be easy to use, and SoundSense wanted us to be able to take it anywhere. System must intake user demographic information alongside data for long-time storage. So like we said earlier, there's a name, there's a reference number. So when this is pulled, their data will come up with it. It makes it easier for us to do this. The system must perform a sync operation to align elements of the noise set, vital signs, and bioelectric signal responses, and recording of the data. So basically what this means is that everything starts at one time and ends at one time. There's no discrepancies at the very end. The system must analyze record data for differences between the baseline data and stimulated recorded data, and we will see this later on when we play our videos. And the system must provide feedback for error detection, so there are no surprises at the end if there is an error. So for our expected budget and actual budget, we initially anticipated that we would have 1% unallocated, which is around $50, 70% for project supplies, so this is different things to replace parts that are broken, so this would be leads, rubbing alcohol to clean, and pads for when we're testing. And then the capital equipment is 0%, so this is stuff over $500. So this would originally be the noise isolating headphones or a computer that can do all the calculations we need. And then travel would be the parking passes, because it's expensive to park here in Seattle. And then the miscellaneous would be different shipping fees and printing fees. And our actual project budget was just the project supplies. So this was the vital signs simulator, which was around $345. And then we have 0% for the miscellaneous travel and capital equipment. And we have the rest of it being put into unallocated because we didn't use any of it.
To best discuss the results of our project, we've included a video demo. We're going to step through the software with an arbitrary frequency being put in, where we show all three bioelectric vital signs being recorded at the same time. I'll have it over to Alex to talk about the graphical user interface.
So the first window that's going to pop up in our app, it's going to ask for a subject reference number, age, and contacts information. It's important to highlight that the only information required to continue with the test is the subject reference number, and this is only going to be used to identify the subject later on. Next, we're going to hit our next button, and we're going to see a window. By this point, it's recommended that the subject is already wearing the headphones, because we're going to adjust the volume, so we can just easily turn up or turn down the volume using the key arrows.
So next, the test system will actually direct the administrator to the system parameter settings. And what this allows us to do is to set the parameters for the baseline collection and the actual test sequence itself. So first, we have the option to choose an audio format in either a WAV file or a designated tone with a certain sound frequency. In this case, we're just going to set the sound frequency to 125 hertz. Next, we have our sound increment and time increment. So during the test sequence, the audio will actually be increased by a certain amount, and we can specify that through the sound increment, which is labeled in dB or decibels. And how often it will, the volume will increase is specified by the time increment. Next, we have our sampling rate, which is how fast we are sampling the bioelectric signals from the subject itself. And this will also correlate to how fast the graphing rate is for the live graphing. We have our duration, which is how long the test system will run for. We also added a feature to scan for nearby Bluetooth devices, since that is what our PCB is connected to via Bluetooth. And lastly, we can choose which bioelectric signals to graph throughout the process. So for this demonstration, we will be graphing EMG, ECG, and EDA. We can go ahead and start the baseline collection with the start button at the bottom. And at this point, the test system will actually give a voice command saying that the bio collection has started. And at the top, we have the EMG, in the middle, we have the ECG, and at the bottom, we have the EDA. And once this ends, the test system will administer another voice command notifying the subject that the bio collection has ended.
The phase we just went through represented that baseline collection, so we were not playing the sound. Oop, looks like we jumped ahead to the next one. The second live instance of graphing you saw was the actual stimulus being applied, so we were actually playing that 125 hertz as we selected 5 seconds and 5 decibels every 5 seconds. We were doing that increase. For best viewing experience, we didn't add the sound to the room, but if you'd like to see that, you're welcome to come over to our booth and experience that. For this live graphing portion, as we were talking about, we're we're giving audio to the user. We're also using text-to-speech to notify the user of when the test is happening, and also test processes that are happening in the background, such as when the test is completed and when the test is saving. Once both phases of the system have completed, we move into the results section. At the first window we see, it represents the baseline sequence. We're seeing all 3 of our bioelectric signs. So that's the EDA, electrodermal activity, which is a measure of conductivity of the skin. In the middle there, we have ECG, electrocardiography, a measurement of the electrical values of the heart, as well as EMG at the bottom, which is a measurement of, electromyography, which is a measurement of the muscle activity. All of those are originally received as arbitrary voltage values from the device. So we bring it into our system, reinterpret in its original format, as well as do some necessary filtering to remove things like high frequency noise from interference in the room, as well as low frequency noise that can come from the interference of other parts of the body, such as breathing, when we collect these. We also do some basic peak detection. Next, we move into the section stats. Here is where we divide this, the actual values into basic sections and then complete a statistical analysis. We're doing maximum, minimum, mean, and standard deviation. Across these various points, we are continually breaking up the sample set so we have a finer resolution to compare against for the results phase. Finally, we are at the least mean squared adaptive filter, which is a filtering method that allows the system to attempt to replicate the original signal. We have the green representing the original signal, the blue representing the estimation, and the red being the error between them. Obviously, everyone is going to be different and have a different bioelectric signals. They're going to have different heart rates. This system works to replicate that, both in the baseline and the results. With that, we can look at how hard our system needs to try to be able to replicate the actual signal and keep in track how much it changes and how much more error we're seeing. That can account for things that wouldn't show up in statistics, such as changes in patterns or bigger spacings that might not show up in means or standard deviations. This represents the results window. So before we were looking at the baseline, now we're looking at all the results statistics. I'll also point out that the section stats are quite zoomed in. If we look, those points are varying between tenths and thousands. Once we have gone through all of the results windows and given a chance to look over at our basic understanding of the plot, we are greeted at the end by a window that will show us all of our statistical information, which will be shown in a second. This represents the super high resolution, all of the statistical information the system has calculated in its full clarity, as well as a statistical difference between the initial baseline as well as the actual test sequence to assign a preliminary flag that can determine the severity based on a percentage difference. So essentially, these ones are all labeled normal as we're using an arbitrary sound, not the intended sound set. So we expect to see a not statistical difference that would indicate a reaction to the sound. We're using those to kind of do a quick categorization as the actual experimentation will move on. Those will become more refined and become more of a structured algorithm to determine the exact characteristics and signatures of certain reactions to certain sounds within that proprietary noise set. Once the test is completed, we're greeted with the test completion page. We can go ahead and close that out, and that will clarify that everything has been saved and the test has concluded. All of the testing information, including those figures, the processed actual information, as well as the raw information, are saved to an Excel file where SoundSense can handle them as they handle their own internal, proprietary, or sensitive information.
So next we have our learning outcomes, and we decided to divide this in two different skills, technical and project management skills. The first technical skill being developing a full-scale application with fully connected backend and frontend code. So the backend code is going to be in charge of creating the sound, playing the sound, recording the vitals, as well as saving them and analyzing them. The front end is just basically the user interface. So drop-down menus, labels, entry boxes, and all of that. Real-time multiprocessing and multi-threading, we use this to make sure that three things were going on at the same time. Recording the vital signs, playing the audio, and also displaying the user interface. We did signal analysis on varying bioelectric signals, which is what Max was talking about, and sound generation with customizable frequency and decibel levels. This was to actually come up with whatever SoundSense wanted to play in the test system. For our project management skills, we have communication within an engineering team. There were a few times throughout the year where we had to change our ways of communicating just to ensure that we had the best possible outcome for this project. And decision-making alternatives, taking into consideration our budget as well as multiple scenarios or possible scenarios. Our next steps are to deliver the application to SoundSense, and this is just going to be us returning the computer with the code and the app that's fully working now. The team is also open and willing to orient the future team that will work in the project to explain how the code works or how to install it in another computer if that's what they want. And all of this will enable SoundSense to transition into the project's next stage, which can include working with live subjects. Thank you for your attention. Are there any questions?
Yeah, hi, my question is, to protect the privacy of, if you could speak about it, the privacy of the subject, is there any measure in place to do so?
Yeah, so as we were talking about in that initial graphical user interface, we have the option to just refer to subjects by reference number when we're creating those individual saves for our sections. Our project wasn't as focused on the security aspect because we were mainly focused on delivering the actual information, all the necessary processing. The actual files are just saved as Excel files in a specified folder within a directory of the program. Those files can be removed, replaced, or deleted in whatever way that SoundSense deals with their sensitive information, as they already have an existing system for dealing with proprietary and sensitive information within their business.
Thank you.
No problem.
Do we have any other questions for the team? Any Zoom questions? Oh, I see you, Joe. Okay.
What was the most difficult task that you had to overcome on this project? It looked like there were several challenges, but if you had to say one thing, what was the most difficult challenge of the project?
I'll talk on behalf of the team. We all face very difficult challenges in terms of implementing our own individual sections of the code, but it was mainly just our first experience working on a full-scale collaborative application that really pushed our team not only to work together, but to make sure that our code was compatible, well-documented, and made sense for other sections. It was written with intent for other people to use and for the future of the project. It was also difficult to kind of clarify our own scope and deal with how far we wanted the application to go, what features were necessary, what came first, and a lot of that kind of comes down to, do we focus on making everything perfect, which is what we're engineers, what we like to do, and instead we had to be reeled back in and focus on making it work all the way through first, from front to back, you know, having a full, have data pass through, recorded and everything, and working on getting those parts tighter, those parts more refined so that our timing was better, our code worked better, and it worked faster. All of that was really just our first time undertaking such a collaborative experience that I feel like we all agree that was one of our biggest challenges.
Thank you.
We do have time for maybe one more question.
So what sort of range of frequencies are you able to output and record?
So we tested from a very general frequency to a very large frequency to extremes. So some of them were not proprietary, but there are proprietary frequencies that are present that we cannot talk about. However, I can say that we did test at a low frequency to ensure that it is actually the frequency, and then we did test at a high frequency within the oscilloscope using a sound interface.
Fair enough.
Sorry.
All right, let's thank the team again. Yes, and thank you for attending these presentations, and thanks again to our virtual audience as well. If you have questions for the teams or you just like to learn more about their projects, please stop by their posters. Poster session right now, it begins now. Thank you again, thank you everyone.
Because it's taking a big problem and using a team of engineers.